Welcome to lecture 9. We're going to be covering materials, and that's chapter 2 of my book. I've invited Dr. Jacob Rome as a guest speaker today, and he today will help us get an idea of why materials testing is so important. And this class, the purpose of this class is to teach you the fundamentals of the analysis of aerospace designs, and that includes aircraft, spacecraft, and launch vehicles. And so far, what we've covered are the failure modes. We've covered the failure investigations. We covered the parts of an aircraft, spacecraft, and launch vehicle design. We showed you the critical areas to focus on for all those structures. And today we start stepping deeper into the material that's required to understand how to predict the failure of aerospace designs. And so for that, I've invited Dr. Jacob Rome. He's our invited guest speaker, a colleague of mine who I highly respect, and is basically my brother from the career standpoint, and as a very good friend. And so Dr. Jacob Rome is a lead engineer, a senior project leader at the Aerospace Corporation, and has advanced research in a lot of areas: composite designs, non-destructive evaluation, additive manufacturing, and has a tremendous amount of interest in further advancing additive manufacturing, including the process, modeling, fatigue, and then looking even at innovative designs for test samples and spaceflight components. Dr. Rome earned his master's and PhD from the University of California, San Diego, and has a bachelor's degree from the University of Michigan, all from the mechanical engineering department. So here I have introduced Jacob Rome. Over to you, Jacob. And here are 5 questions we'll be going through, but if you want to have any opening comments, I go ahead. Over to you.
No, I just like to thank Professor Goyle for this opportunity to speak, and thank the students for coming to listen. And I look forward to helping you guys further your education.
Very cool, Dr. Rome. You worked very closely with the labs. You worked very closely with the labs, not only working in the research arena and analysis of real designs, but you also have helped formulate testing that occurs in the labs. And that's why we invited you. And so I want to just get your perspective why you think that materials testing is so important, especially in the context of composite materials and now the new idea of using additive manufacturing, which is not necessarily new, but is more pervasive now into the aerospace designs. So if you could give us some thoughts on that. I have some slides you provide. I can start stepping through some of that.
Yeah, once you flip to the first one. So the the most basic part here is if you're a designer, if you're an analyst, if you're anybody who's involved in designing or manufacturing aerospace part, of course you start out with you choose your materials and you choose them based on their strength, their stiffness, their high temperature, low temperature properties, maybe their fracture resistance, maybe their impact resistance, maybe just whether they've already been characterized. And with metals, there's 150 plus years of characterizing metal properties, and there's a whole well-defined set of heat treatment parameters and what your in turn your material properties are going to be, and there's ways to verify that. And so for a long time, if you were in metals, you basically said, okay, let's use this material. Here are the properties. Let's go ahead and do it. Composites came along, long time ago, and it was like, wait, like we're realizing that even if I have the same fiber and I have the same resin, I get different material properties each time. Whether I make it at 2 different facilities or 2 different crews, there's been a lot of work done there to get more consistent performance, but you realize early on that you need to test what you're actually building with composites. So that means if I'm, let's say like you have a large sandwich panel there. I think we used to call that the living room table because it was I think it was a 3 foot by 3 foot foam core composite sandwich panel. And like we cut that into smaller segments for testing. Now, when we're doing this testing, there's a couple of reasons you want to do testing. And I'll focus on composites because that's where we are right now. Composites, you want to do the testing because you want to understand the properties of the material you actually have, not the material that another lab made or another manufacturer made. It might be okay when you're the initial design iterations, like to get close enough. By the time you put a part into service, you need to know what the real properties of that part are. Another advantage of testing is you're going through the same process you will when you produce the part. So we had, like we made this panel, we made several others, and guess what? We actually had manufacturing problems that led to less than ideal properties. And so I think we can flip to the next slide. Okay. So like here we have a case. You can see if you look on the left, there's two of these samples with a little step in them, and the point of these tests was to characterize the strength of this part when they have this kind of change in thickness of the foam core. Now, what happened when we made these parts is we noticed they were thinner than the foam was originally, and thinner than they were supposed to be. And so we said, this is a problem. Well, what was going on? Well, it was compression creeping. This is something that occurs during the cure process of a foam core. Is basically if it's under high temperature for a long time, it will creep. Now, there's a way to avoid that, and that's by doing a heat treatment. And this is the lesson learned is we missed that, or we didn't realize how important it was. And so basically we went back, we realized this, and we said, okay, let's go fix this. So we get the parts like the one above. Like the last bullet point there, constitutive testing identified the root cause, and the corrective action was taken to heat treat the foam. So we didn't just like observe this and say, oh, that's what it is. We went to like we did additional testing to confirm that was the cause. So this was a case of, okay, here the advantage of testing was to to reveal a manufacturing problem that we might have run into during production. Now, this was a test program, but you can imagine the same thing happening on a flight program. Is you do the testing early on, you uncover those manufacturing difficulties, and then you improve your process. And I apologize if there's any background noise. Next slide. Next slide, Vinay. There we go. Okay. Yeah. So here was a dilemma. We went ahead and we did the heat treatment, and we saw that these parts are yellow. What's going on here? And then we realized that there's oxidation there. So what happens when you oxidize the material? Well, internally it might make a difference, but what really makes a difference is on the surface. And so then when we did the 3-point bend testing, we saw that like you see here, that's a nice piece of foam core that's being tested there, and it doesn't look like there's anything wrong with it. It has that crack. It stops before it gets to the edge of the sample. If you look down below, you'll notice that all those samples, the defect ran all the way to the end. and we observed that there was failure along the adhesive to the edge of the sample, really saying like we have an interface issue. So we didn't know, we didn't know necessarily like how much the impact was, but we knew it was a problem. Again, like this wasn't something we were going to, it was something we were going to fix. So yes, like we're characterizing it, but let's fix it and know what we really have, because we want to know the capability of these parts, with whether the uniform thickness or they have a step. So we can go to the next slide. And this actually, like you can see the reference there is this was from a paper we gave. This paper was, were there great findings? Do we have some awesome advances? Did we come up with some new test technique? No, we made a few mistakes. We figured out what they were and we fixed them through a methodical method. And it's like, well, that doesn't sound like a good paper. Well, you know what? If someone else had written this paper before, like we might have avoided the same issue. And so the lesson there is, like you learn more in failure than success, and people can learn from your failures as well. So like we looked at the parts, like we had these large parts, and like there was nothing in the NDE that was wrong. So we did tag and testing to look at it, and you can see, like, again, it's failing at that in that yellow part at the interface, which isn't what we want to see necessarily. So next slide. Okay. So we saw, like you can kind of see in the first and second column is, look at the decrease in strength from 1300 PSI down to like 300, 400, 500 PSI. I mean, it was a 75% reduction. And okay, so what did? We actually went and we removed the layer of oxidation, and you can see those numbers bounce back up. And so that was really confirming. That was a surface phenomenon. It wasn't quite as dramatic with the with the shear strength testing, but we knew that we were getting the wrong failure mode, because we like the intent of the test wasn't to measure the interface. The intent of the test was to measure was to evaluate the effects of having butt joints, of having two pieces of foam together and potentially changing the thickness. So yeah, but and in fact, like the last bullet there points out that, like, if we look at the tensile testing, we could predict the shear strength. So like we absolutely confirm that, okay, that oxidation does cause a decrease in tensile strength at the surface, which leads to premature failure. So we go to the next slide. Okay, so that was kind of a look at what can go wrong, and then how do you identify, how do you figure out what went wrong and fix it? And that applies to testing, but it also, like you can think of testing as a pathfinder for manufacturing, and you can see how valuable it is. If we were building flight parts, and we went straight to build the flight parts before doing our, building small samples and testing it, you build a huge part and all of a sudden you realize that you've lost 70% of your capability, and you've lost all that time. And now you have to go fix it after spending money on tooling, like scheduling around it and so on. So yeah.
Yeah, so Dr. Rome, this shows how materials testing early could be very important early in the design process, because if you have the wrong heat treatment, the wrong you don't characterize the properties well, then you could step very late in the program when everything's designed and then get into trouble, right?
Yes, exactly. Like you could design to the wrong values, and then all of a sudden, like you're going to fail your testing. So it's kind of, I talk more about the ladder as a pathfinding exercise, but it's also sometimes you just find that like, oh, this composite strength is 20% lower than I expected. I need to thicken it up a little bit, which early in the design process is not that big a deal. Even in launch, even on satellites, you can absorb a little more weight early in the process. Later on in the process, you've designed everything else around what you're expecting. So you don't want to be, and I would say you want to be surprised early. You don't want to be surprised late.
Because it's costly, right?
Yeah. I mean, you could have the tooling set up. You could be on the launch manifest, and all of a sudden, like if you fail a qualification test, that sets you back a year. If it's a large scale component. I mean, no question. I've seen it before, and it's at least months. And
I like what you said there, and also I want to make sure everybody understands that this is not just for composites and additive manufacturing. This can happen at weld ends in a metallic tank, say, or a more complicated metallic structure. Yep. Sometimes you get large grain sizes in these metals that could yield low fracture toughness, low yield behavior, behave more brittle.
Yeah, and I'll give you an example for that. We've seen this in several times now is with additive manufacturing. Like if you build large thin parts, you tend to get very anisotropic, where your modules can be 50%, could be 50% in one direction versus the other. Not the strength, the actual modulus, the stiffness. And if you don't understand what you're making, like your design is not going to be successful.
Very cool. And so yeah, the next question I have for you, I think you really covered very well, the importance of materials testing. And, I haven't introduced to the course yet the idea of the building block approach, but, what we're really talking about is doing a lot of testing at the small component, small specimens, a lot of them to understand what's going on and characterize a scatter and all of that. But there are a lot of times where some people do not record the failure mode and say the testing failed at the grips, and if you didn't know that, that could be a hit to the scatter in the data, and then you're going to design to even a lower allowable. And so my question to you is, can you give us advice about using high-speed video? Because I know, so you may not know that, but Dr. Rome is a photographer and he enjoys video evidence and all that. So I think, every time we did a test, Dr. Rome was adamant, no, I want to have the best video possible. I want to have the best camera possible, but not because he was just a photo guy, but more because he wanted to combine his photo guy expertise, but also really get the evidence, because that tells you a lot. And so just want to get your perspective on that. I have a couple of videos too as well. So I'm not sure if you want me to play those.
Yeah, whenever we flip over to the first video, this is the same. This is the same test series we did.
And I'll play the next video as well.
What you can see here is the initial failure, and let's just the clue for the first part, where you see that failure is happening on the adhesive, and like for these 3-point bend specimens, like we really designed them to fail in shear. I know there's at least one video that shows that, and so like we probably had enough evidence in this case to see. Like there was a good failure. You could kind of see how it grew shear wise. And it's like, okay, we have good evidence. We know how this happens. We also know how fast it happens, right? Like I don't remember what the speed was, but basically this failure happens at the speed of sound. So it's not like some slow crack propagation problem. It's actually, as soon as the information gets there, it's just breaking. Like it's almost instant, but we could slow down to see 2 frames where it grew. It's like, aha, here it is. It's starting one place. It is moving across. It's almost instant, and that's not necessarily what we would have expected. So this is a good reason why you want the high-speed video, is because you can first see what the failure mode is, right? Like now we know exactly where that started. Like that one might have been obvious, and also know how fast everything's happening. Here it's like that was a proper failure. It just happens quick. And I'll give you an example. I don't have a video for, but there was one program I was on. It failed, 30 or 40% lower than was expected. And we couldn't figure out why. And basically, like they not only had high speed video, but they had digital image correlation, which basically gives you a strain field for the whole place. And this was a cylinder, and you could see like the dome was rotating. And it's like, here actually you can see a delamination form. So it's like, okay, when does the delamination form? Boom, right at the beginning. It's not some like it may be a secondary failure, but it's not. It doesn't happen due to it being reloaded or something. But yeah, so the example I had was like they had a failure. They could determine there was this unexpected rotation between 2 parts, and that basically helped identify the problem, down to its core. And I've seen that in several instances where having the high-speed video really allows you to understand the initial failure, because like mechanics is great. Like we're really good now at predicting the initial failure and even understanding how that will propagate initially. We're really bad at looking at something afterwards and knowing if this was the initial failure or if it happened, 3 seconds later when there was a rebound or something, or even 30 milliseconds later. So the high-speed video is a great way to kind of nail down what the failure mode is.
Yeah, so that's excellent. So I think to summarize what I'm hearing from you, Dr. Rome, is that doing materials testing and recording the testing can give you insights about the failure sequence, which can actually play a role in when you develop allowables, and can also even help you resolve investigations. Did I get it right?
Yes.
Okay. Yeah, so that's great. Thanks for sharing that insight. And then we have this material scatter that occurs. And what I like about you, because I've seen you do that in multiple conferences and working with students, and with contractors, is the fact that there is material scatter. And I see a lot of people say, wow, my analysis is within 1%, but the material scatter is. And what I want you to do is, kind of provide a lesson on that, because I really appreciate every time you bring everybody to the table and say, no. You're probably good to one data point, but not the rest. So could you comment on that?
Sure. I think I have a chart here for that, right? Yeah. Well, like here it's showing some of the scatter. So just talking generally before I get to this part is what we often see in composites a lot, a little bit in additive, even in metals, is your strength can vary substantially. In composites, having a range of 10% is not at all unusual. Like you want to do process control to minimize that, but there's always going to be some variation. So if you go on and you do one test and you're trying to validate a model, you say, oh, I'm gonna I'm off by 6%, so I'm gonna change this on my model so I predict the failure correctly. It's like, well, like, do you really want to do that? Because you don't know if the next test might be 5% high or 5% low. And Vinny knows this. Like if we go to a conference or something and somebody's model predicts within like 2% of their test, it's like, you're like, like you weren't that close. Like I see someone within 2% and I immediately am suspicious. And a lot of times it's true because they will they will tune their prediction to match what they observe. We don't like to do that. What we like to do is like the building block bridge, like Vinay touched on, which is we start with small samples, a lot of tests, characterize material properties, then predict what happens with more complicated tests, validate that again, and then you can make your prediction for the full size structure. You're not regularly going to be within a couple percent. If you're within 5%, you're doing really well after all that testing. If you're within 10%, it's usually acceptable. If you're within 1 or 2%, I don't trust your predictions. so here it's here this is probably actually a better chart of why you want to do testing. Because what this shows here is additive manufacturing. We have parts that if you're familiar with powder bed fusion, you have parts that come off the machine that they're pretty good surface finish, but they're rough. They also haven't been heat treated. They haven't always been consolidated. So generally we'll go through, and if you want to get the best performance, you will HIP it, which is hot isostatic pressurization, which will collapse the voids internally to increase your density. You'll do a heat treatment like this was for Inconel 718 that will increase your strength. And a lot of times you'll polish the surface to get a better surface finish. And you would expect that if you're doing fatigue testing, and like these samples were not, but it's still fatigue testing, that HIP, heat treatment, and polishing your samples is going to give you better results. But what you see here is that your as-built samples actually had the most cycles to failure. The ones that were HIP'd and heat treated had 30% fewer. And this was, I call this post-processing paradox, because by what everyone knows, it's like, well, you have better properties with HIP and heat treatment. Why is it going down? Well, in this case, it turns out what happened was yes, we did do testing and confirm that you have better yield strength, better ultimate strength when you HIP and heat treat it. But these are very thin samples. And it's complicated, but when you have very thin samples, with a crack, you get this plastic zone ahead of the crack. And because you had lower yield strength in the as-built samples, you actually did more work, plus, there was more work in the plastic zone. So there was less crack growth, and you ended up with this backwards. Now, this is important because you might start on a program and say, I'm going to have all 5 of these different kinds of treatments. I'm only going to test the as-built. I don't need to test the other kinds because I know as-built will be worse. And you look at this, you say, actually, that's not always true. It may be true in general. It may be true for thicker parts, but for very thin samples made with AM, and probably very thin parts in general, it just wasn't true. And so this was saying that, hey, test like you fly. If you have HIP and heat treated part, test those. You can also see how much scatter there was. You see that the polishing really reduced the scatter, right? Like we kind of HIP the heat treated polished. Every post-processing step kind of made it more consistent. But it didn't necessarily have a big, in none of those cases, except do we actually get better performance by doing the post-processing? I guess if you did, because you do the HIP first, that makes it lower. You do the heat treatment, that makes it lower, and then you polish it, and it may be lower. It may be about the same. It's hard to say there. But you want to understand that too. It's like, okay, polishing doesn't look like it matters. It just gives you more consistent results.
So to summarize, Dr. Ron, see if I got it right. I think what I'm hearing you say is that when you produce results from a model, or you're trying to do a design and you have some strain gauge data, it is very tempting to go ahead and compare that to a single data point. And your point is more stronger to show your prediction in light of the scatter in the data, because that shows you where, and it can even tell you why you're off in terms of scatter, right?
Yeah. Yeah. Like if you had only done one test of each, you might have found that HIP only was better than as built, and not dug deeper and found this out. So you know, like when we do any test program, we like to do, ideally we like to do at least like 5 repeats, just for, you know, just for experimental purposes, not for characterization. But always at least 3, because that gives you some idea if there's if the variability is to be expected, or if you know, you just, or not.
Right. And so I do have a final question before I open it to the floor. And, you know, I want to cover the idea of what could go wrong during materials testing. You know, one that comes to my mind is, you know, your fixturing is not aligned. And so you could produce results or, you know, bugs. But have you encountered that where maybe the analysis was actually right, but the testing was probably not the right configuration, or the geometry was off, and so
I mean,
everybody's scratching their head?
yeah, I think if you go back to the first slide or so, like one of the early slides with a 3-point bend, um, right there, right there. So I think we added at some point, we added this that little, those little rubber feet there, and we made that wider because, you know, like we didn't look at it initially. I think we had rollers there, and we were getting local failures, and so we actually went and did higher fidelity analysis and said, aha, you know, we need to widen this. Now, that wasn't a problem with the test per se. That was a problem with our design of the test. You know, like we certainly, what you see a lot of times is you see these, you know, if you don't design your test properly, like your loads are going to be too high for a machine. We've seen that before. We've had cameras go out. I mean, stuff happens. I mean, I know when they take that high speed data after the test, I'm just like nervous until they write it to their, you know, the file, and have the have it complete and saved and all that.
And Dr. Ron, I mean, that's an excellent point, because say we did not take pictures of this sample, nothing was taken, and there's no evidence. You could have recorded the value for failure when the rotor was straight onto the composite, and that could have shown a lower reduction in strength. And you may not have
Right.
done the analysis to show there was a problem, right?
Yep, absolutely.
So I
Yeah,
think,
and
to summarize, that the top 5 things we're learning from Jacob today, which are, you know, quite important, and I want to make sure we summarize it before I open it to the floor, 5 to 10 minutes for you guys to ask questions, is that materials testing is important early in the design process, because it can help you um, find issues with the materials, or it could even open up new failure modes you did not consider. That if you were to wait too long, it could impact the design later on, and may become even more expensive by qualification failure. And the second thing I think we learned from Dr. Rom today, and Dr. Rom, please correct me if I'm getting anything wrong, but recording failure modes is quite important, because it can help you understand the failure sequence of events, which can really help you interpreting the results you got. And in many cases, it can help you understand whether there's too much scatter in the data, and maybe some of the samples don't belong because maybe they failed at the grip. Fourthly, we talked about material scatter. Material scatter, you know, there's this tempting idea of taking a model and correlating within 2% of one sample, but the idea here is to really get an understanding of the material scatter and how your model compares to the material scatter instead, and maybe even learn why the material scatter occurred. And Dr. Rom showed the additive results, manufacturing results, to prove that point. And finally, you could have testing issues. For example, he has just shown us the 3-point bend test, where the rotors were applying localized failures, causing a reduction in strength. So new approaches had to be looked at, like using rubber. But again, it shows that even the testing itself can be wrong, which maybe is not the analysis. Sometimes it's the testing also. Is that well summarized?
Yes.
Okay. Any parting thoughts for us, Dr. Room? Any parting thoughts before I have the students ask you questions?
I mean, I would just say if you're designing something, test early, start simple. And like even if you don't think you need to test, sometimes just one simple test can change your approach and save you so much time down the line.
Very cool. I really appreciate it, Dr. Rome. I would like to have students now. I would like you guys to ask questions and challenge some of the ideas here, or even confirm that you agree, or ask questions to learn.
I have a question. Sure. So I asked this question to our last speaker, and I really enjoyed his answer. Could you give us, some time or some experience that you've had in your career that has had, either the largest or a very large impact on you?
It's a good question. Like I think what it was early in my career, like I happened to get stuck working on an anomaly for a very high profile problem, and I was not ready certainly to do any of the work I was asked to do. I probably barely qualified at best, but I did it, and there was a lot of I was given a lot of room to work and grow. And like that experience kind of got me really quick exposure to the different levels, like working in our company and just getting really well practice at, starting out by presenting technical work to your technical equals or superiors really. And then as you move up the management chain, you realize like they're all really smart engineers, but that's not their expertise. And just being able to focus on how to communicate the important findings, not in a condescending way, but in a way that explains the fundamentals without getting caught up in the jargon or the technical details.
Great, thank you.
Very good. Any other questions?
Hello, I have a question.
Go ahead.
I'm actually a part of a mechanical testing project right now. And what we're doing is trying to determine the elastic modulus of this unknown propellant that hasn't really been mechanically tested before, and trying to conduct a test matrix with different kind of variables. So in approaching a new material, or maybe a material there isn't a lot of backing in literature to base off of, what's your process for determining uncertainty, reasonable errors in testing, orders of magnitude of scatter that you're expecting?
I mean, a case like that, I would probably look to see if I could find similar materials. In propellant, you want to find, obviously propellant that has somewhat similar constituents, probably a similar density, and just look at what those values were, and start out by saying, well, it could be a factor 2 higher or lower for your modulus, and I would probably start there for making a first order guess, and then just do a simple test, confirm it or refute it, and then you can kind of like go on. Like what you don't want to do is spend all your time getting ready to, like, because you know what the answer is, getting ready to run one test and realizing, oh, my machine's too small, or the test sample is too thick, right? Because like you're gonna have issues with propellant, like it's gonna be the right size. It's gonna be like you gotta make sure you have the right end conditions, stuff like that. So you want to keep the initial test as simple as possible, because it's gonna have the least dependencies.
Yeah, and I want to add to Dr. Rome's response. I think it's a great response, but I want to also point out specifically something he said, which is there is literature on propellant data, viscoelastic properties, and there's data on the modulus, the initial modulus, tangent modulus, and even incompressibility, because these propellants tend to be incompressible. And so there is data, and if you use the method that Dr. Ron talked about, which is to look at bounds, you're not trying to get it perfect. But I do want to add one item, which is to, before you do the test, do some modeling to make sure that your setup is correct. Otherwise, you may do a bunch of tests and fails at the ends, or you may have some trouble. But dog bone typically is useful. That's why that way you're pushing the failure mode towards the center to some level. Do we have other questions?
Probably have time for one more question anyway, so but I would love one more question.
Yeah, let's do one more question, please. Somebody wants to ask it.
I'll ask. Given your current role at Aerospace, what do you wish you learned when you were an undergrad or in your early career that would have helped you avoid some tough lessons?
I mean, I think some of the like graduate school was a long time ago, and undergrad was really a long time ago. Looking back now, it's clear like I should have. I didn't do an internship. I don't think I worked in a lab when I was an undergrad. I don't think I went to office hours when I was an undergrad. I don't know if you have to do all three of those things, but do at least one or two of them. If I know some people in the summer, they want to go climbing, or they work at summer camp, or they want to cross the country. But if you doing that, do at least one or two semesters volunteering in a lab for class credit. If you have questions, go and talk to professor. I don't think I did that more than a few times, and in retrospect, it seems really silly because, man, I don't think there's much professors enjoy more than engaged students asking complex technical problems. And if you're at this level, those are the kinds of questions you have. And like when I did go, or when I started to do office hours, I realized what I missed out on. So I think that would be my advice: is go to the office hours and try to get some experience either in a lab or by interning in the industry.
Dr. Rom, thank you so much for taking your time and talking to us about materials testing and about career. And why we don't give him a round of applause, like virtual here. So unmute your phone and thank you very much. Okay, I'll continue then with chapter 2, and we're going to cover now the material properties. And why material properties are so important is because they play a key role in the design process, and it helps you characterize material properties early in the design so you can understand the failure modes. Characterizing testing can be crucial early in the design process. Otherwise, you could have late failures that can really hurt you later on. And so that's what we discussed today. And right now, what I want to do is kind of step you through where materials are typically used and why. And so here is an example of a helicopter. And in this situation, the skin and stringers and then the main cabin and other components like this are made with lightweight materials like aluminum, lithium, as an example. And then the darkened colors represent the carbon Kevlar or composite combinations. And the benefit of composites is that they provide the lightweight aspects while giving you the high strength performance. What I want to really talk about here is that when you're designing an airplane or aerospace structure like a launch vehicle or spacecraft, you fully want to understand the failure modes and then select materials in an optimal way. As an example, here's the A380, And the A380 has several failure modes that need to be looked at. For example, CYS is compressive yield strength. E is elastic modulus, which gives you the stiffness. TS is tensile strength, which obviously gives you the strength of the material. And then you have DT, which is the damage tolerance properties. And that can involve fatigue, fatigue crack growth, and fracture toughness. What I want to point out here is that depending upon where you are, for example, here I'm looking at hook tension. Well, hook tension, you're going to have a medium need for tensile strength, but you know you're corrosion sensitive. And then here, where the root of the wing comes and connects with the fuselage, that area tends to be highly loaded by bending moment and shear stress. So I need high strength materials in that arena, that area. And I also, because the wings are going to be vibrating over time, I need to make sure I have good damage tolerance. And I should select materials that are good for damage tolerance. And then you have the fuselage on the back end where you get a lot of compression loading. And so that's why compressive yield strength is important here at the bottom. And so you basically tailor your materials to the various components depending upon the loading conditions and what they may experience in service. So the material usage then, mapping these critical failure modes like tension, compression, yield strength, and so forth, we can map that out into the A380 and further understand the material usage. Here, for example, the fuselage panels were made with glare, and then the fuselage here, the lower fuselage panels with aluminum alloy. Well, the one they chose was corrosion insensitive, less sensitive to corrosion. And then for the center wing box where the wing goes and connects is made of carbon fiber reinforced plastics, which is very strong material and provides you high strength, low weight, limited amount of corrosion, high shear values. Here at the very top, they use a newer alloy, and that was great because it gives you, for the upper wing, a great compressive yield strength. And that's what that material was selected, and plus gives you great damage tolerance. For the bulk pressure head, they used a composite fiber reinforced plastic, and also for the empanages. And so, in the floor structure of the floor structure was also made of several materials. And the bottom line I want to make here is that you are, as a designer and analyst and manufacturing team and testing, you want to fully understand the materials that are available to you, and you want to understand the trades, the benefits of using one versus another. And you want to then insert them in the correct location to give you the best performance for the lowest weight, the highest strength possible. And so here I have another example of an aircraft. And in this aircraft, I'm going even deeper detail, but you can see here that the pink here, for example, is 7150, aluminum 7150. And it gives you great durability and provides weight savings as an example. So you can see here that these are mapped various materials for this particular aircraft. And you can also see that, for example, the upper skin here and stringers are made of 7150 as an example. The fin and stabilizer are made of toughened composites and so forth. So again, you can map everything and really trying to draw a map of materials and what gives you the lowest strength and how you can get the best performance and how to increase durability. Here in this engine, you can see many different materials being used, and you can see titanium as an example. You can see perforated Nomex core, and you can see pitch core. So a lot of composites here. And then you're also going to use high temperature material systems because the engine gets really hot, and I'll be covering that later on. So you also have ECS ducting all over the place. You're going to have ducting, and so for ducting, they'll use titanium as an example here. Bottom line, don't get stuck to various materials. Try to expand your field of view to the various materials available. I also want to point out that the materials for 787 here. So the composites applications, you're going to see composites have increased significantly in aircraft, launch vehicle, and spacecraft design. And you can see here that the majority of this body is carbon laminated composites. In very minor areas are using aluminum, and they're used very, very carefully. The total materials used in the 787 is 50% composites, as an example. So the material usage of composites has increased dramatically and drastically, and it has offered significant benefits. You can see that here, 747, you're looking at 1%, 3%, 11%, 50%, and what increase in the use of composites. And what that does is really give you that lightweight performance, the highest strength possible. What I'm doing here, I'm showing you a diagram. This diagram here allows you to understand the different materials and their cost relative to each other. And of course, these diagrams change over time. So this is only an idea of what's going on with the different stiffness and the cost that you're going to encounter. And so what I want to make sure you understand is that you don't want to use this chart as is. You want to get a little more information. But the bottom line here, you can see the metal alloys are giving you quite a bit of cost, but they give you great stiffness, as an example. Composites are more expensive, and that's shown in purple here. And you can see it's more expensive because this bubble is more to the right, while the metal, spans a lot of this area. Composites are are going to be expensive, not just when you buy the materials, but over the life of the program, because composites do come with baggage, and those baggages can be defects, it can be manufacturing issues, and so forth. And then you have other materials like foams and rubbers and other materials, that will have different modulus, more flexible, but generally aerospace materials tend to be expensive. Here, what I'm showing you is the strength per density against density. And the point of this chart is to show you, for example, that composites give you high strength, but for very low weight. For every pound, composites delivers really nice strength. Ceramics also do a great job. You can see here, very high strength, but a little bit heavier, as you can see. And then you have metal alloys. Metal alloys are very heavy and can give you similar strength performance. Bottom line here, composites do a good job of giving you what you need. Going to wood products and foam, very low density, reasonable strength, but with the environments we see in aerospace applications, they might not be the best because of the moisture issues. The strength versus cost is a very interesting diagram. It shows you a better view of what's going on with aluminum. So titanium, very expensive, very, very nice strength. And high alloy steels and nickel, which are used in engine applications that have high exposure to temperatures, give you very high strength, but very expensive. And then you have your aluminums, which are a very nice choice. They're less expensive than these other ones, but a reasonable strength. And so you're balancing all the time. You're balancing strength and cost and modulus and all these parameters to get the best that you can out of a system. Here, what I'm showing you is strength versus service temperature. And you're going to see here that a lot of ceramics are used for high temperature applications like engines. And composites, when you're using composites, you tend to use them less than 350 degrees F, but it gives you high strength. And so depending upon the temperature conditions you're looking at, you may go with a different material system, whether it's ceramic, glass, or whatever that is. So the material selection consideration that we're looking at here then is ensuring that you are looking at temperature, vacuum conditions, thermal cycling, chemical corrosion issues, galvanic compatibility, atomic oxygen, moisture absorption, and fluid compatibility. So you want to balance all these effects against cost. You want to balance that against strength and modulus. So when it comes to temperature, the range of temperatures experienced will play a large part in the material selection, and that's obvious. Extremes are illustrated by the examples of cryogenic tanks and thermal protection systems. If you look at those systems, they will very clearly use very specific materials to be able to tackle these re-entry loading conditions. Temperature below room temperature generally will cause an increase in strength properties, particularly metals, but that will cause a reduction in ductility, which can be an issue. And you may want to retain ductility. For those cases, you may want to then figure out what to do there. Ductility and strength may increase or decrease at temperatures above room temperature, and this changes depending on many factors. So it could depend on temperature exposure, time exposure, and also then you have the materials being compatible with the thermal environment. You don't want to have a situation where the material is exposed to a thermal environment that can be detrimental to it. For example, composites being used, carbon epoxy being used at 1,000 degrees, clearly the composite is going to have an impact due to being exposed to those high temperatures. Passage through transition temperatures can be an issue, and so those need to be really looked at very carefully. And what I mean with that is brittle ductile transitions, looking at the glass transition temperatures, looking at the moisture effects, and other phase transitions. Thermal cycling can be of high consideration here, and it can induce thermal stresses. You know, thermal cycling is one of the biggest issues when it comes to spacecraft design, because that spacecraft is going to be exposed to the radiation environment and to the cold side, and that difference in coefficient of thermal expansion between fiber matrix composites and the base metal, say I have a tube made of composites, but I also have a tube made of metal, and these two things are connected well, guess what? This thermal cyclic behavior may cause cracking into the composite. And so that could degrade and jeopardize the long-term behavior and performance of these material systems. Materials subject to thermal cycling need to be assessed to ensure capability is retained when you have induced thermal stresses. So very important that we pay attention to that. We talked about corrosion, and again, you want to select materials that are resistant to corrosion. If corrosion is an issue for your case, corrosion will include the reaction of metals, glasses, ionic solids, polymeric solids, and even composites, being connected to other metals. So very important to make sure that the materials we're selecting are corrosion resistant if that is the driving failure mode of concern. Usually you're going to see that aluminum is the first material typically selected for these applications. And if aluminum cannot support the design loads, higher strength materials are typically considered. And that includes titanium or steel. Materials are also selected to specific requirements to minimize strength. And if aluminum cannot meet the performance requirements due to weight, then you could then use composite material. But composites are expensive, and you have to keep that in mind. Low weight is key in meeting aircraft performance goals. And I really want to have materials with higher to strength ratio, meaning I want high strength to low cost materials. And that why is that? Because if I select and the materials that you select highly they're going to impact material selection. And so I want to keep that in mind, because when you're selecting these materials, the choice of the material matters. Not only I want the highest strength, the lowest cost, and the lowest weight, and that turns directly into profits, lower fuel consumption. For a launch vehicle, we're looking here at launching bigger payloads possibly. And so just keep that in mind as you keep moving along in your career. We also want to consider surface corrosion and stress corrosion cracking. Galvanic corrosion of dissimilar metals, that can be an issue. And stress corrosion cracking, especially in the short transverse grain direction, can be an issue. And I will be talking about galvanic corrosion quite a bit. coming up. But other considerations I need to keep in mind is temperature, lightning, erosion and abrasion, impact resistance, and firing, and also cost. And I'm making that bold because you may choose the most advanced system in the world, and you may choose one that can resist everything. But if it's too expensive and it's going to cost a lot of expenses over the life of the program, basically you're probably going to have trouble. And so you want to do a cost benefit analysis and fully really understand why you're selecting the material you're selecting, and is it really that beneficial. The other thing I want to keep in mind and bring to your attention is that when you're selecting materials, you as a designer may have to select materials. Keep in mind that you know your decisions matter. Your decisions matter, and they may play a big role. Galvanic compatibility is one area that people sometimes, as engineers, we forget that needs to be paid attention to. And I definitely want you to think about it. So if I have two or more dissimilar materials, and they are in direct electrical contact in a corrosive solution, or atmospheric galvanic corrosion could occur. The less resistant materials becomes the anode, and the more resistant becomes the cathode. The cathodic material corrodes very little or not at all, while the corrosion material, anodic material, is greatly enhanced. So material compatibilities can be selected in accordance to few standards that you'll find in literature, including the maximum potential differences. In the construction of satellites, two metals that form a compatible couple may have to be placed in close proximity to one another. Although this may not cause anomalies or malfunctions in space environments, it needs to be paid attention because corrosion can take place and it can degrade the properties, and it can be a problem, especially in aircraft and launch vehicle design. So here is a plot, and this plot comes from Mill Standard 889B. And how to use this plot is that you're looking at how these materials can be become a couple for galvanic corrosion. And so in the y-axis, I have which is a column. You're going to see magnesium, zinc, beryllium, lead, aluminum, and so forth. In the x-axis, you're going to see the same materials. And the way you want to read this chart is anytime this material intersects any of these other materials, then you may start having corrosion issues. And so I invite you to look at this later, not memorizing necessarily, but really trying to gain an understanding of whether you could get an impact of high concern. I also want to point out the benefits of looking at other types of plots. So here is based on numbers, and this comes from this materials and process division. But bottom line, galvanic corrosion needs to be looked at. You have to really try to understand what are the interactions. And in parentheses, what you have is a carbon order, which can be important in the galvanic corrosion assessments. Here, what I want to show here is stress corrosion cracking. The way this is helpful is when you're using a material and adopting it, it's very important to understand which material can be a problem for corrosion cracking. You can see here that this is the short transverse, the long transverse, and the longitudinal direction of the grains. And what you see here is L gives you really nice performance compared to the other two grain orientations for stress corrosion cracking. The second observation is that these aluminums in the L direction gives you really nice performance when it comes to that. And so, yeah, so that's how this can be useful is when you're looking at these different materials and these different selection, what really helps is to look at everything together and figure out which is the most common failure mode, which one I'm trying to avoid, and really trying to determine what is the best fit for what you want. And low strength is not always the right answer. Sorry, high strength is not the right answer always, and low cost may not be the right answer. It could be a combination of things that causes you, for that design to pass all these restrictions like corrosion, galvanic corrosion, compressive yield strength, and so forth. There is some cost considerations which I covered already, but I want to show you how cheap aluminum is, and that's why aluminum is used quite a bit. When you go to composites, we're looking at 25 more times the cost. And so, again, something to keep in mind there. Detailed fabrication costs, assembly costs need to be considered, and not just that life cycle costs such as weight and maintenance. I also want to talk about aluminum being used extensively, 80%. Why? Obviously, just showed you that it's quite cheap, but also it's not very heavy and it gives you high strength. And so, especially if you use aluminum alloy and you change the formulation, you can then tackle corrosion, you can tackle stress corrosion, and so forth. Cryogenic applications typically uses aluminums like fuel tanks, primary structures, struts, sandwich structure construction, like the core will typically be aluminum, sensitive to, sensitivity to moisture has to be looked at. And so typically the aluminum alloys can be tailored for specific applications. High strength versus weight needs to be looked at. Aluminum is readily available, so very nice. Low cost, ductile. So that's aluminum is nice. It gives you good ductility. And it's easy to machine or form and provides excellent high buckling strength versus weight. However, it is low strength and per unit volume. I don't think it's completely low strength. I think it does give you some good performance there, but relative to composites, it is low strength. It has poor resistance to galling and wear, and it has a high thermal coefficient of expansion, which could be a problem for thermocyclic applications. And the welding, if you do any welding on aluminum, that can also reduce strength. The surface is susceptible to stress corrosion cracking. That's something I just discussed. Pitting and crevice corrosion can be an issue. And I also invite you to look at galvanic corrosion again. If you're not anodizing, that can be an issue. And so that was that. And what I want to show you now is the alloying that takes place. The alloying that takes place is looking at, for example, combining aluminum with other materials to tackle the issues that I discussed earlier, like corrosion, galvanic corrosion, and so forth. And so here, what I'm showing you is how to read this. And you can see here that there's a number here on this column. And this column tells you what is the dominating material. And so in this case, if it's 2, is copper, as an example. And then and then so forth. And then these numbers here correspond to aluminum modification alloy. And here's a purity or specific aluminum type. So that's how you read an aluminum alloy. So hopefully that's clear. So a lot of alloys are based on aluminums and they're used in primary and secondary structures, in the plumbing particularly, and plating in many applications. And that'll be electronics, thermal control, corrosion protection, and so forth. In addition to standard alloy, more recent alloy developments include the addition of lithium to increase mechanical performance and decrease density. Lithium additions are often lower than other conventional alloying elements. So aluminum lithium alloys may appear within different alloy groups. Reinforced alloys have been used, and that what I'm talking about there is metal matrix composites or hybrid composites. That means I'm interweaving or interlacing metals with carbon fiber composites. You also have the idea of thin aluminum alloy sheets with layers of fiber reinforced composites. I just said that. And a large number of commercial applications use aluminum alloy. And a large number of mechanical and thermal tempers are used to optimize certain properties. For example, I can use different heat treatments on the aluminum to get specific properties. Not all these alloys or tempers are suitable for aerospace applications. So you have to really look at when to use one versus another. Many aluminum alloys will exhibit excellent corrosion resistance in all standard tempers. However, the higher strength alloy, which are of primary interest in aerospace applications, must be approached very carefully. In structural applications, the preference should be given to alloys, heat treatments and coatings which minimize susceptibility to general corrosion pitting and intergranular and stress corrosion cracking. Basically, you want to basically tailor that heat treatment and coatings to basically minimize those susceptible issues. Some alloys are clad with thin layers of pure aluminum, and they do improve corrosion performance. All classical methods are used in the manufacturing. You have shaping and forming processes like rolling, extrusion, forging, cast products. You can also join aluminum by welding, brazing, riveting, bolting, and bonded joints. And that's what aluminum is so nice, is because it's so nice in the sense that you can use it in so many different applications. And I hope that's clear to you. Space, in space we use it quite a bit. The process of metals will give us the rise of residual stresses, which need to be considered, particularly when you're looking at fatigue phenomena. Residual stresses from forming process can be a problem, and they can cause issues like you could also have machining issues, assembly issues like feed up tolerances, and the storage and transportation need to be looked at carefully. Corrosion has to be considered through the whole manufacturer, also including the pre-launch phase, and electrolytic couples should be avoided, and all metals should be suitable protected against external damage by using plating, conversion coatings, paints, and strippable coatings. So very important to keep in mind. This is particularly important in special operating environments, fuel tanks as an example. So I already covered stress corrosion and stress corrosion cracking. I talked about the one thing I want to point out is that in stress corrosion, spacecraft metallic components need to be screened carefully to prevent SCC, which is stress corrosion cracking. You also want to look at materials that can resist long-term storage and sustain high stresses during loading conditions. And why? Because stress corrosion cracking uh, does get influenced quite a bit by tensile stress. So the higher the tensile stress, the more impact on SCC. And it can also cause premature failure of aluminum alloy. Because of metallurgic processing of aluminum alloy usually results in a pronounced elongation of grains, then you really want to look at the susceptibility of grain orientation on stress corrosion cracking. And I covered that a little bit earlier here in this picture. Just to remind you, we look at different aluminum alloy and the impacts on the grain orientation on the stress corrosion rating. So the lower the rating, the worse it is for that application. So I want to make sure that was clear to you, and that residual stresses do play a role, particularly when you're looking at different, whether it's machine or wrought aluminum. Wrought heat treatable aluminum should be mechanical stress relief, so I really recommend doing that. And here, what I'm showing you here is the stress corrosion table. It shows you a list of aluminum alloy, the condition of the heat treat, and basically, bottom line, mechanical stress relieved for these tempers whenever possible. Make sure you're looking at the weldment effects. Make sure that for highly magnesium content aluminum alloys, that we should be using very controlled tempers for resistance to stress corrosion cracking. Alloys with magnesium content greater than 3% are not recommended for high temperature application, and that also is excluding weldments. So certain alloys and tempers are unsuitable. They're not suitable for structured applications in long-term environments, and that includes the ISS, International Space Station. Want to make sure that's clear. Some 5,000 series alloys and tempers are limited to maximum use in the ISS and International Space Station as an example. The 5,000 series alloy has a high magnesium content and requires specific temperatures to provide resistance to stress corrosion cracking and exfoliation. So very important to keep that in mind for that. Electrolytic couples must be avoided and corrected by a suitable insulation between the metals of concern. And by putting that insulation between the metals, you reduce the issues with this issue of electrolytic couples. Sorry about that. Bare metal to metal contact in aluminum is not recommended because that can cause friction, and friction can become a source of ignition. In some applications, not all. But metal to metal can also cause damage to the metal and cause other issues of concern. And so it's important to keep that in mind as you're working towards this. The effects, vacuum does not affect aluminum alloy. All metals in contact under vacuum conditions do fairly well. But under vacuum conditions or inert gas, you get a tendency to have cold weld. And this phenomenon is enhanced by mechanical rubbing. So if you have two metals rubbing, that could make it worse. And radiation at this level does not, in space, does not really modify the properties. When you go hot, it does. It does reduce the strength to some level. But generally, it's not a concern. Aluminum alloy with magnesium contents greater than 3% are not recommended for applications with temperatures that exceed 66 degrees. And atomic oxygen in LEO orbit does not degrade aluminum alloy. So very good to know. I want to step into each of these aluminums a little bit deeper.
Professor?
Hold on.
Thank you.
So aluminum copper varies. This 2001 has a copper ingredient of 0.9% to 6.3%, and there are people looking at aluminum lithium. Typically, you want to keep the temperatures less than 350 degrees C. It provides medium to high strength, has good fatigue resistance, it has low stress corrosion cracking resistance, and these two materials with these particular tempers provide you high strength and can be used for high temperature applications. You have to modify them with the temper, with the heat treat to get you that higher performance. But it may be more expensive. Machinable is machinable, is weldable. It gives you high strength for weldability. And most tanks actually are welded with these materials because they're good for welding. Intermetallic compounds serve as a primary strength ingredient, copper, and the silicon and lithium are added to allow room temperature age hardening, and which improves the ability to forge and improves the strength. There are trace amounts of magnesium and titanium that are present to refine the grain and inhibit stress corrosion. Aluminum 5000 are low to medium strength but easily welded. 5052 and 5056 are primarily used in honeycomb panel cores. You're going to see that a lot. And they can be corrosion resistant, but there are cases where corrosion can be a problem. The 6000 series are low to medium strength and they are easily machined and weldable, but welding does reduce strength. 6061 T6 is most commonly used for stiffness critical designs. The 7000 series is an aluminum, zinc, magnesium, copper, and this one gives you a high strength, but gives you low performance for cryo. So if I have a cryo application, I don't want to use 7000. The brittle behavior becomes quite severe. It also, now the 7000 though gives you good corrosion resistance. But the 2000 gives you better fatigue performance. So you have to kind of select, it's a balance all the time. So let me go back to this table so you can see that balance I'm talking about. Here you can see 7000 did really well in 2000 as well, but it is doing really well for both corrosion and, corrosion and, the stress corrosion cracking as well. So, 7050 and 7075 are extensively used, and you're going to see T73 being used quite a bit for higher strength even. And the 7475 gives you fatigue resistance similar to the 2024 series, and these tend to be used in interstages, whether you're assembling using fasteners. Here, what I like of this table here, and I do encourage you to study that on your own time, is it shows you the various tempers. And it is a very nice table. For example, T1, it tells you what T1 is about. It tells you the explanation of T1 there, the temper. Is cooled from an elevated temperature shaping process and naturally aged to substantially stable condition. It applies to products which are not cold, worked after cooling from in an elevated temperature shaping process, or which the effect of cold work in flattening or strengthening may not be recognized in mechanical property limits. So as a designer, what I think you should do is to look at the different tempers when you're selecting the materials, making sure you have high confidence in the materials you're selecting for the right application. And in here, you're going to see the treatments, the heat treatments they're talking about, and what makes that heat treatment that particular T number. Here are additional temper designations. Here you have T42, 62, 72, 73, 74, 76, and 81. And what is shown here is the heat treat for various conditions. And I invite you to pause the video and kind of study this on your own, and even do a print screen if you can, and kind of digest. Now, I'm not going to ask you to memorize any of this because it's not expected. But when you go to industry, I think what's going to make you successful is to understand where to get the information. You don't always have to memorize the data. If you can, great. But if not, it's important to know where can I go to get the data. So this is one good resource for you to keep in mind when you're looking at aluminum tempers. Here at the bottom, you will see stress relief tempers, and it gives you additional data there. T51, T510, T511, T52, T54. And for example, here is an interesting one. T252 is basically is a 3-digit designation, and may be any thermally treated major division or temper designation. But here's a 3-digit number, is 252. And what I want to show you is that this one is stress relieved by compressing. So you apply a stress relieving by compressing after heat treatment or cooling from an elevated temperature shaping process to produce a permanent cess of 1 to 5%. So clearly here you have some mechanical loading and you also have some temperature application. And so each of them are going to have various conditions on how you process the material to get the stress relief that you need for that application. Here, what I'm showing you is the aluminum comparisons. I'm showing you the comparisons for the various classes of aluminum. Here I have 2024 T3, T351, and T42. These three here give you high strength in tension and gives you optimal fracture toughness to slow crack growth ratio. You also have 2324, which gives you 10% improvement in strength over 2024 T3 with increased fatigue and fracture toughness. You also have this 7000 series that I had discussed earlier, great for high strength compression, high strength, better higher strength than 2024 T3. But the issue with this 7000 series here is that it gives you low fracture toughness. This particular one right here gives you great SCC, stress corrosion cracking, and better fracture toughness than T6. And my point, guys, here, ladies and gentlemen, my point here is to pay attention because the temper can completely switch around the behavior of the material when it comes to the fracture toughness, corrosion resistance, and so forth. And you also have the 7451, which gives you better properties than 7351 as an example. Here, what I'm showing you now is a comparison of the various aluminums that are commonly used and is reproduced from the Mill Handbook 5J, which you should have now. And I'm showing you the density column. I'm showing you the modulus, the shear modulus, the Poisson ratio. What you observe here is the modulus is fairly constant across all materials. the shear modulus, and also the tensile modulus is fairly constant. So not a lot of change there. The density is almost the same, but the Poisson ratio is also the same. But look at how me changing the aluminum formulation and the sheet thickness quickly changes the yield strength. So here you have 16, here you have 47, and if I go with 70, 75, 70, right? The ultimate strength is 78 here, you can see that there, but it could drop all the way to 30 or 62 or 42, depending upon the formulation we're worried about or looking at. You also have the ultimate shear and then the ultimate bearing capability. And you can see here that sheet is 121, very nice strength for bearing there. And then the other ones are lower in value. What I'm doing here is I'm basically showing you the same information I showed you here. And what I want you to do is to pause the video here in this particular plot and further increase your understanding of how these different metals compare. But bottom line that I did not show earlier is that aluminum lithium gives you is lighter 10%, is stiffer 10%, and gives you fatigue performance that's superior than other metals. But it is expensive, and it needs to be considered in your assessments. I also want to point out 7178 T651 that was not covered. Great for compression application, but a higher strength than 7075 for sure. And so copper are really using electronics a lot, and the main application for coppers are electrical subsystems like wiring and stuff like that. You're going to see a lot of the classifications for that. So you're going to see brass, which is copper and zinc alloy. Often you're going to see a lot of alloying going on, and they can be used to act as a lubricant for machining operations, and also bronze, for example. Electronic assemblies use wires made of high purity copper, and beryllium copper is used quite a bit in electrical connections for low temperature applications. But the thing I want you to pay attention is that this is great for that, and it does give you great corrosion resistance. But the issue is safety, and it is hazardous. So copper is also used as a matrix phase in some reinforced metals. The processing and assembly of copper. So in electrical assembly operations, copper wires are typically soldered to terminals, and that requires a correct selection and use of the materials to get there. The beryllium and copper are heat treated to optimize mechanical performance, and they're usually done to be able to produce a material that can be formed, machined, and joined. Beryllium oxide tend to be toxic, so the process methods that are used does require quite a bit of safety equipment, especially if you're going to do heat treatment, welding, or machining. You better start looking at some important safety equipment because of the toxic behavior. Copper, for example, here, the point I want to make on this slide is that they are sensitive to stress corrosion cracking, and the corrosion conditions can occur, and it can cause the loss of zinc. You could also have issues with, stress corrosion cracking, which is the point I wanted to make. So this slide is just trying to pay attention, bring that to attention. That stress corrosion cracking is an issue for copper. On the space environment, the vacuum does not present any problems for copper, so easy. All metals in contact under vacuum conditions or inert gas have the tendency to cold weld, like aluminum, and radiation does not modify the copper alloy behavior. And temperature problems are similar to those encountered in technologies other than space. So again, copper at high temperatures will produce lower strength and more ductility. But you may have other issues as well related to thermal contact and vacuum, and Yeah, so atomic oxygen, which is present in low Earth orbit, will attack the copper. Nickel and its alloys, and I'll be covering this a lot in the next couple of slides because it's quite important. These are used for high temperature performance and because they're really good for corrosion. Some alloys of this kind are used in electrical applications, and few alloys uh, are really good for controlled expansion and constant modulus properties. So, like bimetals, thermostats, glass ceiling, and so forth. Others have been developed for specific applications, and there are a number of alloy that are used for welding and brazing filler materials. I also want to talk about nickel plating that's also used in a lot of applications like electronics, thermal control, and corrosion protection. Nickel alloy are applied to systems requiring corrosion resistance. And I want to cover the fact that they're used for high temperature applications. And the main use of commercial pure nickel is in platings. You're going to see that a lot, and it provides a corrosion protection. Electroless nickel can also be hardened to produce abrasion resistance while retaining the corrosion resistance. Nickel also provides elevated temperature corrosion resistance to many acids. And as it is for magnetic, care is needed in its use in some applications. Nickel-based materials can be grouped by principal alloying additions. However, alloys within one composition group may be used in more than one general application group. And there is this idea of hot corrosion that occurs, and you're gonna have resistant deformation and fracture under imposed surface stresses and temperature, and that includes creep resistance or superalloy. Almost all heat-resistant nickel alloys are developments of the basic 80 Ni 20 Cr composition. And you also want to make sure that on the thermal cyclic conditions, you are making sure that we are protecting the oxide layer. Otherwise, the oxide layer could crack and spall. So the protective oxide layer can fail, and you want to be careful about that. Nickel alloy are used for grip resistant applications and typically engine applications, turbine blades, for example. Turbine blades, you're looking there at creep and corrosion oxidation requirements, and so that's where nickel can play a big role. It also provides great toughness and fatigue resistance. You could use it in discs, so just like turbine blades, for very similar reasons. And you're gonna use them at areas where you have high temperatures, like 550 C. And many of these alloys will also have great cryogenic temperatures. That nickel is expensive, but gives you really nice performance for when you need it. Very nice stuff. And here I show you some pictures of cooling channels, and you can see here um, areas where nickel alloys could be used. Here's the blade of a turbine behavior material. Here you can see the various materials on the considerations. You can see ambient air in these areas, aluminum here, and titanium in certain areas. But why? Because I have high temperatures. Super alloys here because I have huge temperatures going on there. But I like this plot because it shows you how the materials are mapped to the various temperatures. And yeah, turbine blades are quite critical, and you have to know how to design them and how to use the materials. So here I give you some sort of a guide so you know where to go. Very nice picture here showing further the usage of these materials with more care. Here also I show you the pressure as a function of axial station and the temperatures, again showing you very high temperatures, but keep that in mind, this comes from Rolls-Royce. But bottom line here is at these temperatures where I have high temperature applications, nickel could be the way to go. Different materials used in Rolls-Royce jet engine. In blue, titanium is ideal for strength and density, so that's where you see the blue. but not at high temperatures. And so here I have the high temperatures, and in the red areas, I use the nickel superalloys. In orange, you can see little orange, you use steel because they're great for static parts in the compressor area. The other colors could represent composites or something else. So continuing on here, that's how you'll go ahead and map the temperatures to the various materials. I like this plot too because it shows you the different components of an engine. It shows you where it is and what temperatures you expect. It's not exactly giving you the value of the temperature, but the bottom line is that a particular engine could have 3 to 5 materials, and they're chosen to tailor and survive various loading conditions. For example, a compressor is going to see up to 550 degrees C, but I need strength data up to, I need the strength to be as high as 550 MPa. The combustion chamber is going to be weakly loaded, so it's not going to have a lot of loading, but the gas temperature is high, and the air cooling is also high. And but the limiting factors is corrosion and thermal fatigue. So what material will be good for that? So that's how you want to think about it. Turbine discs, and you don't have to do everything on your own. You can work with a material scientist. One thing I want to point out is when you're working on designs, you don't want to work alone. You want to work with people. So you'll confer with the materials team and say, hey, I have these loading conditions. Which materials could be good for that? Now, you don't want to fully put that onus on them, but you also then want to verify that you agree that that's a good choice. Turbine disc up to 750C. The centrifugal force can go up to 500 megapascals. And so you do need a high yield strength for that. And the turbine blade is actually highly complex. The feeder modes could be cracking. You have high stress, high temperature, high yield strength, high creep resistance, and so forth. So again, using materials that are the right ones. People are also Rolls-Royce, for example, and across the world, we're internationally looking at improving materials because if you can get to a single crystal material, you can increase the performance on the blade microstructure and really have good strength and everything else. And you can see that here. If I have a single crystal, I have better corrosion resistance, better thermal fatigue resistance, and better creep resistance. So there are people looking at pushing everything to the right to then give you the performance I need for engine design. Any questions so far? I'll continue then with titanium, which are generally chosen for their mechanical properties, the great temperature resistance and chemical resistance, expensive to keep that in mind. Conventional titanium alloys are used for primary and secondary structures, fasteners, and also used in plumbing systems. Titanium alloys are normally selected for strength properties and depend on a number of specific heat treats like hardening, quench, and temper. The most commonly used titanium alloy is titanium 6A, aluminum 4V, and it is extensively used because of the mechanical and corrosion property data that's available. It can act brittle, so you have to be careful. You can use all classical methods for the forming and shaping. The titanium can usually be welded very well, braced, riveting is great, no issues with bonded or bolting. And not all alloys can be braced, but it's fairly flexible. Some metals and processing chemicals can degrade the properties of titanium, so keep attention to that, especially stress corrosion and hydrogen embrittlement. And you could also have the issue of reduced fracture toughness due to these two issues. The fatigue life of titanium alloy is reduced by fretting at the surfaces, and structural design should definitely want to avoid fretting. You have situations where above a particular temperature, the oxide film will break down and the small atoms will start embrittling the metal. High temperature processing methods are done usually under vacuum and under inert gas. During production, the selection of appropriate processes and avoidance of surface contaminations are vital to avoid property degradation. And also, corrosion has to be considered very carefully during the whole manufacturing and pre-launch phase. This is particularly important for special operating environments like fuel tanks, for example. Titanium alloys are susceptible to hydrogen embrittlement, and they're unsuitable for hydrogen environments where you have hydrogen. So care needs to be taken to clean fluids and other chemicals using titanium um, because of concerns with the performance of these cleaning fluids causing a degradation in strength in these titaniums. Surface contaminants which can induce stress corrosion, you need to really look at that carefully. People don't pay attention to these stress contaminants, but they can actually produce stress corrosion and hydrogen embrittlement. And it can also reduce toughness. So you want to pay attention to hydrochloric acid, cadmium, silver, chlorinated cutting oils and solvents, methyl alcohol, fluorinated hydrocarbons, and mercury compounds containing mercury. So this is some of the ones that could be an issue from the surface contaminants perspective. Steels are quite a bit used, actually quite a bit. Stainless steel a lot, but let's start with steels. They're expensive, very heavy. They're used for very specific structural items where high strength is needed, like the rocket motor casings, bearings and springs. Bearings because of the hardness that I need, springs because of the durability that I need. Steels are based on alloys of iron and carbon, and all contain some level of other elements like carbon steels and manganese. Alloy steels contain one or more additional alloying elements to improve properties and workability. And the tensile strength of plain carbon steels increases with carbon content up to 0.8%, and it reaches a maximum value of 900 megapascals. So something to keep in mind that that tensile strength can be improved and is directly related to carbon content. And it does give you a decrease in ductility. So when you increase carbon, then you're trading off the high strength with the the lower ductility. Hardness increases progressively with carbon content. So you can, if I have bearings, I need to play games with, not play games, but basically select the carbon content that I need to target a hardness. And it helps with the hardness and wear resistance. And so you can add alloys to, you can add carbon steels to produce a wide range of alloy steels, and which improves the performance. Tensile strength is attainable from alloy steels, which depend on the composition. And another thing I want to keep in mind is that for some hardened and tempered items, such as ball bearings, you may want to use very high strength steels, like 1250 megapascals. When you exceed this value, typical stress corrosion becomes quite a bit of a concern. So something to keep in mind as you're selecting materials in your design. These maraging steels or martensite aging steels contain Ni, and with a various additions of Cr, Co, Mo, titanium, aluminum, and very low levels of carbon, you can achieve very nice benefits, very high tensile strengths, high toughness, and ease of heat treatment and machinability. They're also very nice for, they're very highly expensive, and so that's a trade-off there. So most conventional process techniques work well, no problem there. Heat treatments may be applied to the bulk of the material to selectively harden the surface. And a wide range of compositional and mechanical surface treatments are available to improve surface properties, like shot peening, thread rolling, and stuff like that. And you want to make sure that when you're using the high strength materials, you're caring for the machining used, and that we're not introducing new failure modes related to the microstructure. Carbon and alloy steels tend to be really good for stress corrosion cracking below this particular strength. Anything larger can start causing you trouble from the stress corrosion standpoints. Some steels do have ductile and brittle transformations, so something to keep in mind there, depending on the alloy composition, and can occur with the normal service conditions for some space components. Some alloys do exhibit poor weldability, and some alloys are prone to corrosion in atmospheric and acidic aqueous solution. Low alloy steels, depending on the composition, tend to have a better resistance to corrosion, atmospheric corrosion. High alloy steels, however, do show an improved resistance to atmospheric and marine environments. So this is very good to know. High strength steels are also prone to stress corrosion cracking in the seawater environment and other chloride solutions. Stainless steel is a variation of steel, and stainless steel is actually used quite a bit in aerospace applications. They are corrosion resistant, that's one reason. And there are a number of properties that are nice. They're creep resistance and good fracture toughness resistance at low temperatures. And yeah, so it has great magnetic and thermal characteristics. The use of stainless steel is used a lot on engines, and you may see that on spacecraft as well, particularly storage or tanks. And some components may use it in their thermal protection systems, and also some places may use fasteners may use it as fasteners because they're highly reliable and they give you high strength bolts. And so here, I wanted to show you with this chart that there are various types of stainless steel formulations, and there is the austenitic, the ferritic, the martensitic, and the precipitation hardened. And each of them will give you different outcomes. For example, the ferritic gives you really nice increased strength obtained by heat treating. And then the austenitic gives you strength that's increased by cold working. So you can see that each of them gives you an increase in strength, but through a different process. Like the precipitation harden is through a heat treatment process. And my point here is that, I mean, I want to use a positive either there and kind of look at this on your own. But bottom line, the different kinds of stainless steels will give you different behaviors in the environment. So you want, for example, the precipitation hardening, you want to pay attention to stress corrosion cracking, as an example. And for stainless steel, you want to make sure you're cleaning the surface carefully, as an example. And austenitic tends to be resistant to stress corrosion cracking. And some grades of stainless steel could be susceptible to hydrogen embrittlement, and it could be picked up from the processing. So let's discuss metals usage in launch vehicles and aircraft. Titanium, for example, has better strength to weight ratio compared to aluminum or steel, but it will cost 5% to 30% more by weight. And it does have good corrosion and temperature resistant properties. And annealed titanium provides good fatigue and damage tolerance. Typical alloy titanium, in this case, can be either annealed or solution treated and aged. And there are challenges with welding and machining. And there is a low coefficient of thermal expansion for titanium, which can be a good thing if you were to have thermal cycling. And it is used for attached fittings to composite and fasteners. There's other metals that are used, for example, magnesium alloys. They're great for stability and have a high heat capacity. They're weaker but lighter than aluminum. However, they have the same strength to weight ratio, and they exhibit poor ductility and poor resistance to corrosion. They can also be susceptible to ignition during machining, and due to this volatile behavior, magnesium alloys may not be used. Beryllium alloys, I already said this before, is toxic, has low ductility, and fracture toughness is low and is not weldable. It has high stiffness to weight ratio and high thermal conductivity, so it is attractive in other ways. Stainless steel, I also cover, is corrosion resistant. It performs well at high temperatures, and the 300 series will be used a lot on spacecraft. The 400 series will be used in magnetic applications at low temperatures, and it is brittle. 440C is often used in bearings because it has high hardening, and it does very well for high contact stresses. The nickel-based alloys, they use a lot A286 and Inconel for aerospace fasteners due to the corrosion properties. Invar is used to bond composites due to having a low CT. So you're going to be seeing very often that Invar is used in a lot of applications when it's bonded to composites because of that great low CT that it has, so that the coefficient of thermal expansion between the composite and the Inconel, that mismatch is not as large, and so therefore you don't produce stresses that could be detrimental in that bond line. But it is very heavy like steel. Here are alloy designations for steel, which have greater strengths than titanium. And steel is limited and is used in highly loaded components such as landing gear because it's heavy. And so here are the different alloy designations you will find in the Mill Handbook. Carbon steels, low alloy steels, intermediate alloy steels, high alloy steels, precipitation and transformation hardened steel, stainless steel. And here are the various combinations, and they're all quite used. And then you have your AISI type 301. Here I'm showing a comparison on various steels. And what I'm showing here is a number of them with the tensile modulus, again, very similar. The shear modulus is the same, the Poisson ratio is the same, but where the differences lie is this yield stress. And you can see here the yield strength for some of this material can vary quite a bit. The ultimate tensile strength as well, and the ultimate shear as well. And these in order, an increase in order, so you can see the benefits. Now this came from Mill Handbook 5J, and it provides quite a bit of information, as you can see. The ultimate bearing capability is also higher as you go down this table. The thing that's very interesting that I really think you should check out is the density, the modulus, and Poisson ratio is the same. And one will say, well, if these characteristics are the same, why you have these other things going on that change quite a bit, and they're related to strength? Well, because the different materials are processed differently. And you can see here the bar, forging, and tubing produces quite a bit of great performance when it comes to yield strength and ultimate strength and so forth. Titanium comparisons, here you can see three of them being compared. And again, similar density, modulus, and Poisson ratio. But when I look at the yield strength, you can see variations there. And clearly the titanium has great properties here, these two right here. When I compare materials across the board, what you notice is that graphite epoxy, for example, has great tensile strength compared to any other properties. And when I look at the density is quite low compared to any other material. So clearly composites offer that strength to weight ratio benefit. Aluminum does very well, but you know, the key ingredient here is taking the ratio of FTU, which is a tensile strength, divided by density to fully understand which of these are more efficient. You can see here, this stainless steel, yes, provide great strength performance, but the modulus is high and the density is at least about 5 times greater than graphite epoxy. But it has its own benefits. And stainless steel can also be used in a lot of applications. Here is even a more comprehensive comparison of materials. And with this, setting the stage, now that you understand the data, here are the materials: aluminum, titanium, steel, nickel, beryllium, magnesium, fiberglass, Kevlar, graphite, and these are your composites right here at the bottom. And what they're assuming here is that the composites are 60% fiber content. When I look at this first column, what I see is a room temperature data at tensile strength, the tensile yield, the yield strength, the compressive yield strength, and then the modulus. And you can see here the density of the various materials. And what we're doing here is taking the ratio, so exactly what we talked about, taking the ratio of this to density to see what's more structurally efficient. When that is done, and I take the ratio of tensile divided by density, what I get is this value here. You can see clearly that one of the greatest tensile strength per density is steel in general, but also composites by quite a bit. If I took the modulus divided by the density, again, you can see composites doing really well. But composites are expensive, so you have to start trading between the different materials and then deciding what is best for your application. And so I want to discuss now some of the material selection ideas here, looking at more top level view. The aluminum has low density, is efficient in compression, is easy to machine, is ductile and tolerant to concentrated stresses. It also does really well when it comes to high strength to weight ratio, but it does have relatively low to strength per volume and low hardness, so it's not good for bearing applications. High coefficient of thermal expansion is a problem, because if I were to bond it to a composite, then the high coefficient of thermal expansion in the composite doesn't have hardly any. That mismatch could cause high stresses when exposed to thermal environments. The steel is high strength, has a wide range of strength, hardness, and ductility, so you can get it by different treatments. But the advantage is that it's not very efficient, and it is hard to machine, and it is magnetic. There's also your heat-resistant alloys, which are high strength, has high strength per volume. Strength is retained at high temperatures, is ductile, is not efficient for stability, and is not as hard as some steels. Magnesium is low density and is susceptible to corrosion. Titanium is high strength, low coefficient of thermal expansion. It is expensive, hard to machine, and has poor fracture toughness. So you will often see a lot of issues with titanium when it comes to fracture. Beryllium has high stiffness versus density, and the disadvantages are low ductility and fracture toughness, low short transverse properties, and is toxic. Composites can be highly tailored for high stiffness, high strength, has low density, and is good in tension. The disadvantage is costly for low production volume, requires development program, and the strength depends on the workmanship. So you have to do a lot of work here. It's expensive, and laminated composites may not be as strong in compression compared to these other metal materials. It can be brittle, so and it can also be hard to attach. And here again, I show you a different view of material selection. Here in the first column, I show aluminum 6061, A286 bar steel, and titanium. And what I'm doing here is showing the data in different ways. This is adapted from Seraphin. You can see here the corrosion resistance is great for all of them. The weldability is not bad, and the machinability is not bad. So I selected great materials to compare. And what I want to show you, the Poisson ratio is typically about the same. Modulus, can vary quite a bit. The density, obviously steel is more dense than aluminum by a factor of 3 or 2.5. But you get higher strength, as you can see, compared to aluminum. But it is heavier. And so then you have to start figuring out what do you want to do. Titanium has low CTE, so that's a good thing. And the properties are actually quite robust for having that kind of density. So you'll see this titanium used quite a bit in applications. The Mill Handbook 5, which I invite you to download, contains design information on the properties of metals for aerospace application. The handbook was first coordinated with the Air Force, Army, Navy, and Federal Aviation and Industry. The data that's contained in here, it contains material strength, including typical values and statistically derived lower bound design allowables for a lot of stuff, for tensile yield and rupture, compressive yield, shear rupture, bearing yield and rupture, elongation to break, tensile and compressive Young modulus, shear modulus, Poisson ratio, density, thermal conductivity, heat capacity, and thermal expansion coefficient. So all this data is provided in the Mill Handbook. It's very helpful for designing. You can download it. The latest version now is called MMPDS, and that's the version that will contain the latest when it comes to the material properties for the various materials. In my book, I go into some of this stuff. Wide range of tempers of commonly used metals is included here, and is usually given for various thicknesses because the heat or age effects can affect the metal differently depending upon the thickness. Given at elevated or cryogenic temperatures for various exposure times, they also provide plots for temperature adjustment factors, stress strain curves, a lot of great information that's provided. The handbook on material selection for launch vehicle is given here. It's a great document to read. It provides an extensive summary of knowledge concerning the corrosion, stress corrosion cracking, fluid compatibility, flammability, toxicity, and thermal vacuum stability properties of aerospace materials, both metallic and non-metallic. The Aerospace Structures Metals Handbook contains a lot of data there too, and is worth taking a look. And it provides cross-reference to a number of materials, and it even provides great online database. The lessons learned, which is a lesson learned gold from the space shuttle, and I'm just giving you a fact, is that riveting was not compatible with graphite epoxy due to inadequate impact strength. So that was a trouble. And then due to galvanic corrosion, it was not possible to use aluminum fittings with composites, so a titanium was used instead. And this goes back to some of the things we talked about, and I decided to include some of those details here. I want to point out that the material properties depend on the grain direction. And so here you can see a machine bar forged block. And you will see letters here. So you will see A, B, and C. A is longitudinal, B is long transverse, and C is short transverse. So L, LT, and ST. So in the A, you see longitudinal. And for machine bar, this is how the properties are going to turn out and how the grain will be oriented. The extrusion is going to have very similar to the machine bar, but you're going to have an area here that has properties more like short transverse. And then in this direction, is going to be different from the machine bar, where you're going to have a long transverse going that way. And then in this direction, you can get you're going to get a short transverse. The sheet plate and rectangular bar hand forging is going to look like this, with A longitudinal going that way, B long transverse, and then the short transverse. And here you have the machine die forging. Again, this will look very similar to the extrusion one, and you'll have C properties across or near the parting plane. The die forging is going to have very interesting properties. You can see the grain orientations there. And then for a bar that's extruded, the A direction or the longitudinal direction is going to go that way. The thickness orientation is going to be short transverse, and so forth. So why this is important, because that's going to help you determine which material properties you're going to be selecting, and being cognizant that those can change quite importantly. I also want to point out here what a typical Mill Handbook 5 example looks like. I'm just trying to show you here, what does it look like? So here, what is being shown is a 7075 aluminum alloy. It gives you the MS spec, and then it gives you the form. So you have the sheet and the plate styles. Then you have the temper materials, and then you have the thickness. And so you can then select what is the most appropriate for your application. And then for the basis, you have the S basis, A basis, B basis, and I'll be going through that later. But these are strength values for design. And A and B correspond to a statistical value. So instead of taking the average of the test data, you design for some statistical value here. And that's what A and B means. You also will notice that the data is given in the L direction, LT, and ST. So very important consideration. And so now what we have here is we have here the tensile strength, the yield strength in all those three directions, the compressive yield strength, and then I can keep going on. Here's the bearing strength, for example, for E over D 1.5 and E over D of 2.5, 2.0. And E is basically that distance to the hole, and the hole has that diameter. So testing was done to try to come up with that. And then you have the bearing yield value, and then you have the basically the elongation of the material. And you can see here that here for this thickness is quite brittle, 3%. Well, it does very well here for the plate T65-1. Here, this column here with 9%. So that's not too bad. That's ductile. 3% is brittle typically. The modulus is provided, and the compression modulus is provided. The shear modulus is provided along with the Poisson ratio. Physical properties are also given in various figures throughout the document. And, you know, they also give you some highlighting. They will highlight for you specific things. For example, there's a superscript here, B, and that superscript B, what it's saying to you here, and it's actually pointed to some of these ones here, is telling you that this specific alloy, temper, and product form exhibits poor stress corrosion cracking resistance in the grain direction. It corresponds to an SCC resistance rating of D, as indicated in table 3. So you have to go through that and better understand what is going on. The bottom line is there is corrosion issues, and it gives you more information about that. It doesn't always, it's not always consistent, but it's worth looking at that. Here the sheet materials are rolled flat, metal thickness less than 1/4 inch. They're typically used for fuselage skin frames, ribs, spar webs, control surfaces, and pressure domes, and do have a good grain orientation. The plate, which is a rolled flat metal thickness greater than 1/4 inch, so for the sheet it's less than 1/4 inch, but then here we're greater than 1/4 inch, and you can see the thickness of these plates. They're typically used for wing, tail skins, monolithic spars and ribs. Fittings and grain orientation can be a problem. You can see here that when I go to plate, I start to get some brittle behavior, but sheet has great ductility in general. And so, yeah, it can get some trouble. The grain orientation can be a problem. The extrusion process is usually produced by forcing metal through a forming die at high temperatures to achieve the desired shape, but usually requires additional forming and machining. You have stringers, ribs, spars, caps, stiffeners, and the grain is aligned in the lengthwise direction, this direction. And that is used for stringers, ribs, spars, caps, and stiffeners, and that will give you an idea of what material properties to be using. Forging is produced by impacting or pressing the material into a shape. You have large fittings for that, large frames and ribs, odd shapes, controlled grain orientation. Residual stresses can cause warpage, and tooling is a challenge. So there are some challenges with forging, especially residual stresses and the tooling that's required, but usually used for very complex shapes. Casting is produced by pouring molten metal into a die to achieve a particular shape. And these are used for very complex shapes, typically has poor fatigue and damage tolerance properties, and there is a high tooling cost associated with casting. You're gonna have some issues with casting, and typically there's a casting factor that's applied because of the potential low confidence in the properties in general. And so for that reason, it's important to pay attention to casting as a potential concern. And it is used for complex geometry, however, like nacelles, engine components, and propulsion components such as valves. So very, very important. And it is neat to see that casting is available, but it does come with trouble sometimes. Upper wing cover, the upper wing cover skin, typically 7075 T651 aluminum plate. Stringers are 7075 T6511 aluminum extrusion. Not always, but is an example. And after machining, you get age creep formed to T7351 or T73511. It's compression dominated. That's why it's good. This material, it reduces the compressive yield strength and greatly increases stress corrosion resistance. So that's the benefit of this upper wing cover. The skin 2024 T351 aluminum plate is tension dominated. That you will use in tension dominated situations, good for ultimate tensile strength and superior fatigue and damage tolerance. And that's why it's great for that. And the stringers are aluminum extrusion, and you have a high ultimate tensile strength and good damage tolerance properties. So I want to make sure you understand, here's the upper wing cover. You can imagine the wing lifting upwards so that the upper wing is under compression. And that's why we want something with good compression yield strength. The lower wing cover is under tension because the wing bends upwards. And so then it makes sense I need something tension dominated and good damage tolerance properties. And you can see here some images of that. Spars are 7050 and Z7451 aluminum plate, high tensile and compressive strength in thick sections, and good stress corrosion resistance. Fixed threading edge surface, typically graphite epoxy fabric, composites in general, secondary structures typically used there. We want something with good stiffness, which is why composites are typically used. The leading edge is typically 2024 clad aluminum and is corrosion resistant and polished for appearance. But most importantly, it is heat treated to T62 after stretch form into shape. But I do want to point out that we want to make sure that is used here in the leading edge because of the corrosion resistance. And since there's de-icing that occurs in this area by hot air, it is a good material. Also, it has great resistance for impact damage like bird strike. And so that's why you'll often see 2024 clad aluminum being used there. The landing gear support beam tends to be a very heavy duty material, titanium and neo forging, low fracture properties, but very high strength and stiffness, and is used in a lot of these lug designs. The wing to body attachment here, typically you have a high strength requirement because you have this wing carrying the whole weight of the vehicle, and that's attached to the body. It has a great corrosion resistance and is used in lug designs. The flap tracks very often are steel bar and high stiffness is required for floater and geometry, and again, good corrosion resistance. So some notes about metal material properties. Typically you have, and you've seen this before in other courses, so I'll be glancing over this a little bit and providing some context for the most part. But I want to point out that you will typically have a machine, and the machine applies a loading tension that measures the modulus and Poisson ratio. And then you have strain gauges that measure the strains, and you apply a force here, which is measured. There's a fixed head, and then you have the grips here for holding the specimen. And then here's where you have your strain gauge, and you then apply a load to measure the stress strain curve. Typically, it will look like this, a specimen 8 inches, ½ inch in diameter. Typically, that's what it will look like. And then towards the grips, 3/4 of an inch diameter. And what we're trying to do is drive the failure towards the center. The tension testing, it is then performed to obtain modulus and Poisson ratio. What you do is you take the force measurement divided by the cross-sectional area, and then you know the strain as a direct measurement. So that gives you stress versus strain. And then the curve will typically look like this. And then a 0.2% offset on the strain, you draw a parallel line to this here, and that marks your yield strength. And that's useful because if you didn't have the 0.2%, it would be kind of arbitrary to know where the yield strength is really occurring. So engineering applications, typically you will see that. And then as you go further through the stress strain curve and you were to unload, you may have some amount of permanent deformation. The Poisson ratio for metals, ceramics, and polymers can vary anywhere between 0.25 and 0.4 and can be measured quite quickly. So hopefully that's clear to you. And so I'll continue here saying that it is important to take note that the stress strain curve is going to vary from material to material. For example, here you can see the stress strain curve for magnesium, very, very ductile. You have the structural steel here. You have aluminum alloy here. And again, all these can vary quite a bit depending upon what material you're looking at, and the behavior here at the very beginning of the stress strain curve could also look very different. Some of them exhibit quite a bit of hardening, and you can see that in this curve right here, which is a nickel alloy steel. This one is more like elastic plastic, so it goes yielding and then becomes quite plastic right away. And that's, for example, steel water quench tempered at 700 degrees F. Here you can see the yield strength, and it kind of compares them as you move up, with steel being the highest. A very interesting graph to see the different shapes you can have for stress strain curves. A lot of them can be found in the new handbook. Here, what you can see here is the response of the metal as it's been loaded. And you can see that as I increase the stress, you will start seeing some necking if it's a highly ductile material. And when it reaches to this point, that necking becomes so severe and the cross section so deformed that the structure fails. And we look at that, and that's the area reduction. The greater the area of reduction you have, the more ductility we're talking about. And more importantly, more importantly, the elongation and the area reduction will go hand in hand. So the higher the elongation, the higher AR typically. Here you see the ductile behavior, how necked it got. But if it's brittle, say it fails here at the beginning, 3% strain, then you get very little necking and very little elongation and very little area reduction, and you just get more of a brittle failure. You can see here the curve of brittle versus ductile, where brittle fails quite a bit quicker than anything else. And so moving forward here, we look at the ductile fracture. The ductile fracture is going to have some cavity formation with initial necking. Cavities will form from cracks, and then you'll have crack propagation and then final shear. The true stress strain curve is an important thing to keep in mind, and I'll explain that. But basically, the true stress strain curve versus the engineering stress strain curve, there is a difference there that I want to explain. So in the true stress strain curve, you're looking at the loading applied divided by the area at that particular point. In the engineering strain, the true strain is given by the logarithmic of the actual length of the sample divided by the original length. What you may have been more used to seeing is engineering stress strain curve, which is stress equals F over A naught, and epsilon and A naught is the reference area that I started with. So the force is always divided by that original area. The strain is the change in length of the sample divided by the original length. And my point is, very important point here is that some finite element codes require to provide the data in true stress strain curve. So if your data is in engineering stress strain curve, it needs to be changed to true stress strain curve. Now, some codes require engineering stress strain curve, so that means that you have to bring back the true stress strain curve into this format. So very important consideration that I think you really need to pay attention as you're working the various problems in engineering. If you make any of these, if you make an error here, your results will drastically change and you may get into trouble. And it may not be very, very pretty. You want to make sure that we know what we're doing. Now, this strain here is this epsilon n, so you can convert from epsilon to epsilon t, the true strain, using this formula. So if I know this, I can calculate epsilon t. So that's one way to do that. The Ramber-Osgood model is used to fit the stress strain curve. And so in the Mill Handbook, you can get a stress strain curve for these materials, and the Ramber-Osgood allows you to specify the yield stress and N, the exponent, the hardening exponent. And so that's going to allow you to curve it to some of the stress strain curves for ease in finite element simulations. And you can see here the exponent N, how the stress strain curve behaves because of that. If N equals 1, it behaves linear, but that's unlikely. You're going to have more of these kind of behaviors. Hardness testing is very important. Is a good way of measuring the resistance to indentation. Like ball bearings will be under high contact stress as an example. So hardness testing can be very useful. And there is various tests that are done to study that. You have identers like this that push a material onto the metal to see how much indentation you get. There's also balls that are pushed into the material and so forth. And it will measure the resistance to localized plastic deformation. The harness testing, you know, you're gonna have most plastics, the harness will start from very low from most plastics and increase to the highest value, which could be diamond. The scratch harness is used. The indentation harness is Rockwell, Vickers, and Brunel and Shore. And there's other ways to look at harness. Larger harness means, so if I have a larger harness, say like nitride steels, you have smaller indentation, and the resistance to plastic deformation or cracking in compression is much less, much greater resistance to plastic deformation. And better wear properties as well. And here it shows you for the various testings, Brunel, Vickers, which is micro indentation, Noop, which is also micro indentation, Rockwell and superficial Rockwell. It tells you the denter type. Here's a sphere, and so forth, and then the top view of the denter. And then it shows you the load applied, and then how to calculate the hardness number. This hardness number can be translated to strength in some way, and it can be used very successfully for even forensics, if you're not sure what material you had or something like that. Or if you want to find the in situ properties of a metal after being machined, this is not a bad way. For example, say I have a harness testing and I have a 10 millimeter hardened steel. I can use the HB equation here, 0.102 F divided by A. If it's been applied as 10,000 newtons, I calculate A based on this formula, where D is the diameter of this denter, which is a sphere, and D is how much plastic deformation was left. So I can calculate this, plug it in here, get HB, and I'll do, you can take the same metal and do 3 different tests. You can apply that load, but you want to keep 3 indentation diameters away so that the previous marks are not involving anything. So that material displaced is not affecting your results. Hardness can be related to tensile strength. For steel, the tensile strength is 3.45 times HB. And you can see here how I'm able to take HB, the hardness, and convert that to a tensile value. The tensile strength can, it's correlated with the Brunel hardness number. You can see that here. A lot of testing was done to show that. You can see that for steels is this curve, for cast iron is this curve, for brass is this curve. So every material will have a different curve here. But the important thing is you can use a Brunel test to then, basically the Brunel hardness number can be correlated to tensile strength. So not only you can measure the strength through a test like this, through this instrument machine here by applying a tension load, but you can also measure it by performing indentations into the material, which is quite exciting to see that you can actually do, and it can be used in forensics. Composite materials, I'll be touching this very briefly, but I have laminated composites, which are made of multiple plies. And then I have sandwich structures that will contain a face sheet and a foam core in the middle. These materials, you'll have either laminates or sandwich structures. The core can be aluminum core or foam as the core. And the fascias will be basically plies are stacked together at different ply angles that are tailored to give you the maximum performance you need. And what I'm doing here is comparing the stress strain for the different fiber systems that exist. And all I'm trying to show is that, for example, number 5 is carbon. IM7 has great strength, but it's low strength to failure. 2 is S-glass, great strength, but also great strain to failure. Number 7 is graphite. You can see how brittle it is, and it hardly has high strength, and it's very low elongation. So again, just like with metals, you can balance and determine which are the best materials that I need for my particular application. When I look at the specific strength divided by a specific and look at versus specific modulus, what this is showing you is that pound per pound, what has the best behavior. You can see here that most metals are down here, so low strength, not as good modulus, but when I compare to composites, superior strength and superior modulus. And when I go to fiber metal matrix, I potentially have even higher modulus per weight. In boron aluminum, for example, gives you very high strength as well. Carbon epoxy is heavily used because it gives you really nice strength and it's actually pretty good stiffness. You can see other polymers down on the left side. Composite materials versus metals. I covered this before, but this is a nice plot showing the quasi-isotropic graphite epoxy with a specific gravity of 1.8 with an ultimate strength of 276. And you will say, well, that looks very similar to aluminum. And the point I want to make is that if you don't tailor composites, you may not get the benefits that you may need, and it may not show up as much. So that's why it's so important to tailor composites and not just default back to some materials. Ply angles are just standard and they don't really, they're not tailoring anything. The whole point of composites is to stack the ply angles in such a way that you get the best performance you can out of strength and modulus with the lowest weight you can. And so quasi-isotropic is not always the right answer. And you can see that here, I'm not getting a lot of benefit. Yes, there's a weight reduction for the same strength, but it's not a humongous change there. Here, what I'm showing you is for composites for different carbon epoxies, the tensile strength, modulus, and strain to failure is similar information I showed before, but showing you for glass epoxy, Kevlar epoxy, carbon peak, and carbon phenolics. And the nomenclature for the carbon epoxy, you're going to have a bunch of different materials for carbon epoxy, like T300, IM7, AS4, IM6, and that kind of thing. You can see here the IM7 with great tensile strength compared to anything other than carbon peak. And then the modulus is also really good. And the strain to failure for IM7 is remarkable. And glass epoxy is really good. And Kevlar epoxy is really good. Kevlar is used for impact damage like bullet vests in impact situations. Composites in general, you have the fiber matrix, which is carbon epoxies, glass epoxies, Kevlar epoxies, fiber reinforced thermoplastics. And the usage, for example, of carbon epoxies is that it's used for materials in composite structures in aerospace applications. They're using trusses, pressure vessels, optical benches, racks, and they're available in low and intermediate and high modulus forms. The damage tolerance typically varies inversely with modulus. And glass epoxies are used in pressure vessels and sacrificial layers, and mostly as sacrificial layers. They're used as flame barriers for carbon epoxy structures. And also you'll see glass epoxies used as a barrier for galvanic corrosion between carbon epoxy and say aluminum components. Because I said before that you could get some amount of issues with galvanic corrosion. Kevlar epoxies, like I said before, is excellent for damage tolerance. They're used in pressure vessels, small side rocket motors, and applications such as impact events. In such impact events I'm talking about here is in essence like a bullet vest. Fiber reinforced thermoplastics, you have excellent damage tolerance, good repairability, and lower structural performance thermal sets. And then you have your phenolics that are used for high temperature applications like nozzles, fairings, nose caps, and re-entry vehicles. Impact damage, what I'm doing here is showing you the maximum impact load that was applied and the compression after impact. And what I want to be able to have is a situation where when I have an impact event at a particular energy level, that the compression after impact is not greatly reduced. And so you hear IM7, you see here IM7 does really remarkably well. The compression after impact is large. So after impact the part and I apply compression, you can see how IM78551 does very well. And that's the kind of material you're going to be seeing used a lot, quite a bit. So composite materials versus metals. I want to make that comparison more deeply because there's this conception that composite materials is a way to go for everything. And my point is you want to compare and see for that application whether it's worth it. For example, for fatigue, clearly on the top, I'm showing you the graphite epoxy compared to aluminum. And you can see clearly that graphite epoxy has many more cycles to failure compared to aluminum. For example, at 75% of the load, I have, a lot more life than if I were to look at aluminum. The advantages of composites is that they're high strength, high stiffness, they can be tailored, great fatigue life, as I showed here on the right. The dimension stability is awesome, corrosion resistance, and low thermal expansions for space applications, which is great when you're exposing materials to thermocyclic behavior. Disadvantages is that with composites, you get a lot of manufacturing variability, a lot of types of defects that are hard to analyze, and there's workmanship sensitive issues. You have complex mechanical characterizations, it's complicated to repair, the degradation of structural properties under moisture and temperature occurs, and there's poor energy absorption and impact damage. It's expensive and complicated to inspect. So you can see that not everything is rosy with composites, but you definitely want to pay attention to that. So continue on here, what I want to cover is the kinds of testing you can do. And I don't want to go very deep into this because there's a composites course that I teach, which you can access. You can access some of the material here on my YouTube channel, and there'll be future recordings on this topic. But for now, what I want to make sure is that you understand that there's a lot of testing that needs to be done, like Dr. Ron mentioned, that measure the tension, the compression, modulus, Poisson ratios, the shear, and fracture mechanics. Typically for composites, you want to characterize 9 independent constants, the modulus in each of these directions, the Poisson ratio, and the shear moduli. And for unidirectional lamina, you really just need to characterize 6 properties, the modulus, the modulus in the other 2 directions. This E11, E22 is in plane, E33 is out of plane, and these are your Poisson ratios. Shear modulus also need to be characterized. For plane weave, you also have to characterize 6 independent constants, and plane and unidirectional are going to look like different when you see what is equal to what. Other composites architectures may require characterization of all 9 independent constants. So here is how you will measure the modulus in the 0-degree orientation. So here you apply a load in this direction, and again, I'll be glancing over this because there's a composites course where I go deeper into this, but I want to make sure you understand the fundamentals here. So I apply a tension load to this, and I measure the strain. So I put 2 strain gauges, one going that way and one going across. And so what I'm showing here is the thickness, but also the width of the sample. And typically 6 plies is what's used. And what you see here, I want to make sure you understand that this is not what I'm trying to point, these are the grips here on this end. And so you apply the loading conditions, and here's a 0 degree, which is this, this is not the thickness, this was meant to be the width. And then the here one is 90 degrees. You can see the plies going across. And this width is 25.4, and they use 8 plies instead. So the thickness is greater than when you look at the longitudinal test. The bottom line I want to make is that when you do this test, you get E11 for the 0 degree test. For the 90 degree test, you get E22, and then you get the Poisson ratio nu to 1 by using the strain gauges. From the 0 degree test, you get nu 1 too. And so you can then check the results to make sure everything makes sense. You plot the stress strain curve, and the ratio of these two curves really gives you the Poisson ratio. It can also give you the strength to failure and elongation to failure, both in the 0 degree and 90 degree orientation respectively. Sorry about that. So longitudinal compression testing, typically you may do a 4-point bend test where the center here in the middle, you get only compression stress. Also, you have this sample where this is the IIT-RI test, and this is the STM3410M03. And in this test, you apply compression loading into a column. And the C393 test is this one on the right. It's called the 4-point bend test. This test, if you strain gauge this, gives you the compression modulus at the top, because when I apply loading, it's in compression, and that's what this test is doing. And then you'll measure F1C, the strength in compression and the strength of failure in compression, because you expect compression failure from this test. You can also do in-plane shear test, and the in-plane shear test measures G12. Here's an off-axis test. In the off-axis test, you put strain gauges in this direction, and you can then output the shear modulus. So you can then plot the stress strain curve and calculate the shear modulus out of this data. Here, the ply angles are plus minus 45, and so that's why it's called the off-axis test. And this test is amazing, gives you the data you need, but it tends to overestimate the strength by 20 to 30%. So there are better tests, and those tests are the ISO-PESCO test, which I will not be covering here. That's covered in the composites course. Out-of-plane tension test can also be tested to measure E33 out of plane. So my plies are stacked in these directions, and I'm looking at the strength in that direction. The Poisson ratio can be measured, and the out-of-plane elongation as well. Here, what I'm doing, pause the video. I'm not going to go into this into a lot of detail, but if you want to learn more, pause the video and download the ASTM standards through the university libraries, and you'll get these ASTM standards. They're typically used to measure various strengths and elastic properties and strength parameters. And every test will be different. For example, the longitudinal test I covered, the transverse tension test gives you the E22, longitudinal compression gives you the compression. So I covered all this, but just trying to bring to attention that you can download these ASTM standards for further study. In a more advanced composites course, are going to allow more detail into that, and some of that material is in my YouTube channel. For interlaminar shear, this is more for quality. You will do a 3-point bend test. The through thickness tension test is a relatively new test by Northwestern University, and provides the E33 and the strength in that direction. The through thickness compression also is a good test. It gives you the compression modulus in that direction. And then the through thickness shear is the ISO-PESCO test I talked about, that I'm not going into details in this particular lecture. I invite you to also then pause the video now and download this material qualification and equivalency for polymer matrix composite materials. Great reading for you to read and to learn. So when I'm doing testing, and I'll let you go download this and read this material, but when I test composite materials and I'm looking for qualifying the materials, I want to have multiple batches, I want to have multiple lots, and I want to have multiple samples. And here what you see is the number of specimens per test condition, and for the different kinds of testing that I would like to see to get the properties. For example, the tensile strength in the 0 degree needs to follow this ASTM standard. And I need to test this at cold, dry, and room temperature dry, elevated temperature wet, elevated temperature dry, because for composites, the strength can change depending upon whether the environment is dry or moist, or whether it's cold or hot. And so something to keep in mind as you develop a test matrix, make sure it's comprehensive, that you have enough test samples to basically calculate in allowable, which I'll be discussing very soon. There's other composite testing that's done, such as fracture testing. Here, this testing is the double cantilever beam test, and these tests measure the fracture resistance due to applied loading. And fracture toughness is a material property of composites, and it can be very beneficial for assessing delaminations in composites. Anytime you have a defect, you can then use this kind of approach to assess it. There's also the notched laminate testing to characterize fastening joints. You have the tension or compression with or without fastener. We call this open or filled hole tension test or compression test. And then you have the bearing test and compression after impact test. So a lot of testing for composites is required to fully characterize composite materials. And as Dr. Rom said, if you were to make a laminated composite at location B and laminated composite at location B, the properties may not be the same because there is there could be an influence from the manufacturing process itself. So keep in mind, as Dr. Rom said, measure all the samples prior to testing and verify the correctness of the ply angles. Take photographs of the failed samples, and failure mode should be consistent, because if you have failures in the wrong location and then you have it out of scatter your data, it's going to impact your statistics. You want to have sufficient number of samples, at least 6 at each critical temperature. The more samples, the better, and to ensure that all the failure modes are consistent. We also recommend that you test at least 3 lots as driven by program requirements to determine lot-to-lot variability. And I also suggest that you look at multiple batches as well to gain confidence in the data. You can also eliminate outliers in data using statistics as long as there's strong justification for that. So how do you do that? So if this is, say you have a set of samples, Xi, and X bar is the average of all the test data, and S is a sample standard deviation, then what you need to do is to make sure that MNR is greater than the critical value. If MNR is greater than the critical value, then you have to declare that. You may have to declare it as an outlier, but you cannot just throw it away. You have to have the evidence that that's the case. So for example, I have 18 samples. 18 samples gives me 2.652 as the critical value. So if MNR for that particular sample Xi minus the average divided by the standard deviation such that this value is greater than for 18 samples of 2.652, then that may be declared an outlier. So yeah, so something to keep in mind there, that you definitely want to pay attention to that. You cannot just throw the data. You have to have evidence that something went wrong with that particular sample. Here, as an example, I'm showing you 18 samples actually, just in fact, and the raw data is given here. The average of this data is calculated, and then you take the standard deviation and calculate the MNR. You can see here is 2.663, and 2.663 is greater than 2.652. So this may be declared an outlier, but you have to then study that deeper. Secondly, I want to point out that this is the cold temperature dry, the room temperature dry data, and you're doing this critical value calculation for each condition. Cold temperature dry, room temperature dry, elevated temperature dry, elevated temperature wet. What I want you to notice here is how the strength decreased when I went hotter. And that's typically true for composites. When you go colder and room temperature, you may not see that impact as much, but when I go hotter and wet, clearly wet and hot conditions will cause a strength reduction. You can see that here, the 100 PSI dropped all the way to 56 PSI or so. Statistical strength allowable. The design values must be chosen to minimize the probability of structural failure due to material variability. And so when I design a structure, I don't design it to fail at the mean value or the average strength. That makes no sense. you want to make sure you're designing against a statistical enclosure. And two types are used, A basis or B basis. A basis, and this is discussed in my book extensively, A basis is for single point catastrophic failure with no load distribution. So A basis is used for any location in the structure where if you had a failure, you can lose the whole part. While B basis is used for redundant load path, meaning say I have 5 trusses that take load, one of the trusses failed, but the other 4 can take the load just fine. Well, then B basis is fine with that. If I have the 5 trusses and I lost 1 truss and all the system breaks apart because of that lost truss, then A basis is important to be used. A basis allowable is used to enclose at least 99% of the population material values and is expected to be equal or exceed this tolerance bound with 95% confidence. So single point catastrophic failure with no load distribution, this is the way it's going to look like. The way you calculate A basis is this value is equal to the average of the test samples. So you have 10 samples and the average is 50 KSI, that 50 goes here, minus the standard deviation of those 10 samples times Ka, which comes from a table, which depends on the number of samples. So if I have 10, I'll show you very soon what Ka is. For B basis, very similarly, that's 90% of the population material values, and it's expected to equal or exceed this tolerance bound by 95% confidence. And here, what I want you to notice is that A basis is going to be lower than B basis. A basis is more strict, and A basis will be lower in value than B basis. Okay, so something to keep in mind. And so if I were to design to A basis, then my design will be heavier. If I design to B basis, my design will be lighter. So you have to trade to see what you want to do. The second thing I want to point out, if the scatter was too large because you didn't record the failure mode and it fell at a grip and your scatter is large, you can see here how your A basis gets impacted. So your standard deviation will be larger, your A basis will be lower, and I have to design against that strength. Well, that strength is lower now because I had too much scatter in my data because I retained that one data point that may not have been a good data point. But I had to retain it because I didn't have any evidence to get rid of it. So clearly, it is important to pay attention to all of that as you move forward. Here is how you calculate this K factor, this Ka and Kb. You come here to the one side of B basis, and if I have 10 samples, I'll plug in a 2.355 for Kb. If I have 10 samples for A basis, the K factor is larger. So you can see it's 4. And so if I put 4 here versus 2.6 here, you can see clearly that the A basis is lower, so my design will be heavier. However, that will be the case if I have a single point catastrophic failure point. So you have to basically balance your design and see what's more optimal in the design process. So a lot of things have to be considered. More clearly stated here, if I have a Gaussian distribution, that clearly the Gaussian distribution, normal distribution, is a good representation of my data. The average is here. I calculate the standard deviation, and the B basis will be somewhere there. And so the 90% of strength values from population will be greater than this value with 95% confidence. Now, this 10th percentile should go more to the left, so this kind of got messed up, but that's fine. My point is I'm just trying to explain what it looks like physically. So say I have an example. I have a B basis example. So I have a tensile test, which was performed, and I gathered 6 samples. So 120, 125, 110, 105, 112, 127. The average is 116, so you can use Excel for that. The standard deviation is 8.82, and Excel can do that. You can use a lookup table for 6 samples, and so I go here for 6 samples. B basis is what I'm looking at, 3.007. So then I take the K factor of 3, and so the B basis is 116 minus 8.82 times 3, which is 90. So I don't design to the average. I design, in this case, I'm designing to B basis, 90 KSI, which is obviously is enclosing 90%, with 90% probability, 90% of the population with 95% confidence. So how to determine the margin of safety of a system? So the margin of safety is basically the allowable that I calculated here, 90 KSI, divided by the factor of safety, which is specified depending upon whether it's an airplane, an aircraft, a spacecraft, launch vehicle, and so forth, whether it's manned or unmanned. And then the stress comes from the finite element model, or you do a hand calculation, as you've learned before, -1 greater than 0. So this has to be greater than 0 for the structure to be adequate. You often want to keep a pocket margin of 10% for non-conformances, or even 15%, to make sure you have enough design margin for any issues that you may encounter, like thicknesses being too thin and things like that. If you don't have that, you may run into trouble and a repair may be needed. The factor of safety is included for the purpose of accounting for uncertainties in the analysis, variability in the manufacturing process, and as I've discussed before, it can help with the unknown unknowns. So here's a practical application. The following are the values for a particular program. Program X uses 1.5 factor of safety. The tensile stress is predicted at maximum operating conditions of 72 KSI. The B basic strength allowable, which I had just calculated, is 90 KSI. And the question is, does the design have adequate structural margins? So the margin of safety is that allowable of 90. The factor of safety is 1.5 for that program, times the stress calculated from the finite element model, or the hand calculation, 72, -1 is -16%. So the design is not adequate because I have -16%. Now, that does not imply by any means that design will fail. It simply means that the design does not meet the specified safety factor requirements for this program. In this case, what is recommended is to redesign it and or have the program evaluate the risk of having a failure in this location and assess whether this negative structural margin can be accepted through a waiver or some way of maybe you do testing or you find ways to get happy with it. But that is not the ideal scenario, and you definitely want to address it because the factor of safety is there for a reason. So you can also evaluate the probability of failure by plotting the stress as a Gaussian distribution, material strength, and then wherever this curves intersect, we call that the probability of failure. So the structural reliability is based on probability calculations, and they're typically detached from the factor of safety. I would say there's two ways to look at the problem, from the probability of failure standpoint and the factor of safety standpoint. And in the industry, we use a factor of safety approach, but the probability calculations are typically used in situations where you have negative margins and you want to show to the program that the risk is not as large as the negative margin suggests. The issue with the probability approaches is that the inputs to produce these curves are not very well defined sometimes, and you don't have all the data for that. Industry experience also suggests that the probability calculations out of these curves tend to overpredict the structural survival. And that's because you're going to have issues in the design that you didn't account for, and your probability calculations may not include those. The structure continues typically to be designed with a factor of safety, and we typically do not rely on the probability of failure calculations, which I'm not saying don't do, but just keep that in mind. And here is an example of the number of occurrences for predicted flight loads and the predicted failure loads. And so bottom line is that you're just trying to keep space between the predicted flight loads and the predicted failure loads. Keeping that space increases the chances of success in the life of the program. So I hope you have a great day, and I hope you enjoy this lecture and that you understand that material properties become a very important point in the design, because it can drive cost, it can drive schedule, it can drive the weight even, depending upon how you treat this moving forward. And then, just as Dr. Rom said, any issues you may have, if you don't do enough testing early, it may come to bite you later in the program. So have a good day.